Alright, let's see if we got it going. We're back. We're back. Looks like we're going. Alright. Gonna start off thanking, as always, thanking the members. Thanking everybody that makes this stream possible. And we're gonna go live. And we'll pull this down a little bit. Make sure it's not too loud. But hopefully you'll be able to hear it at least. Welcome back to the stream. This is Jason Watts. My name is Jason Watts. If this is your first time on, welcome. I am a founder and CEO of a little automation company out of the southern US called Alpha Industrial Technologies. I have about a little over 20 years of experience working with Siemens drives and technology. And yeah, I'm here to work with you and hopefully expand your knowledge on Siemens technology and be able to get you to where you understand this kind of crazy world a little more day by day. I appreciate everyone, again, that supports this channel. There's lots of different ways that you can support your channel. The easiest way is just to like and subscribe. And I know it sounds kind of crazy that or it's kind of annoying, like YouTubers always sitting here going like and subscribe, but it really does help. Like when you like this stream, like if you're coming in right now, go ahead and like it. And we're going to be going for a while today. And just by you liking it, will get YouTube to come out there and put it out to a few more people. And the more people we get involved, the more people get to the love of Siemens automation. And you know, that's what you want, right? But yeah, I appreciate all of the people that are part of this growing community coming in and really, really constantly just being supportive of everyone that comes in. Saif is definitely one of those guys. What's up, Saif, in chat? If you're joining us live, be sure to drop a hello when you come in chat, where you're from. If this is your first time here, everybody, welcome to here. So yeah, we appreciate everybody that has been part of this growing community. And yeah, so it's been a couple of weeks, or I feel like it's been a couple of weeks. I think it's been just a little over a week since I did the last live stream. And I know that seems like a long time because we've got all of this information that's been bottled up. But if you didn't catch the short that I posted, it's all for a good reason, because I was learning some new stuff, learning about Cinemeric. And if you don't know what Cinemeric is, man, it's some good stuff. It's some cool CNC equipment that's put out by Siemens, and it is quite powerful, quite robust. And honestly, it's like if you come from the CNC world, you understand kind of like how to use the equipment and what's there. If you come from the PLC side, I feel like you kind of understand how the equipment works, but you know nothing about the CNC equipment. And that's where I was. I'm like, okay, I know PLCs, I know the drives, I know motion controllers, so how does this stuff work? And coming in, not realizing a ton of stuff that is taken care of you or taken care for you. And that system is just amazing. So that's where I've been. I've been up in Chicago, Illinois, or just outside of Chicago, and been doing that Cinemeric training. And so we're definitely going to be having some live streams about the Cinemeric product portfolio. I don't know, I know about a week's worth of information about Cinemeric now, but I realize I feel like I could be a bridge and kind of from a PLC perspective, talk to you about how that system works, and we're definitely going to be talking about that. But today we're doing tales from the help desk, because the past couple of weeks we have had a lot of activity in the help desk channel of our Discord. And if you're not familiar with our Discord, there is a link in the description of this live stream for you to join up and join up. It's a great, we've got a couple of channels, great growing community of like-minded people that are from all over the world working on different problems. And yeah, we've got a couple of people that I wanted to definitely thank as a part of that help desk channel, and I gotta make sure I get their names right because we had a couple of different things that we've been working with over the past couple of weeks, and we have. Let me find them. Let me find them. I thought I had them written down, but I guess not. Because I wanted to thank everybody that is active in that channel, because it's not just me that has experience. We have everybody has their experiences that they can like help each other with, and we've got a couple of things to where in real time we had one of our channel or our long time kind of partners and community members. His name's Lucid Dream. He was working on an issue that I don't think I caused his original issue, but we were kind of like discussing through this, and we had Furcho in the Discord helped him out and was like working with him on that and trying to figure this stuff out. And we also have channel member LFC 27, who is actually a member of the channel, and they're constantly on there along with Lucid, helping each other out. And we all have something that we individually can contribute to kind of like everyone's kind of issues. And yeah, the motion control topics are there. We're definitely going to talk more today about some different motion control topics, and yeah, we will try to touch on we'll definitely be doing a motion control 102 class. We did a 101 class a couple weeks ago, and it kind of got us up to kind of the general topics about what motion control is about. And so Samir, when we'll definitely be doing more in depth about that, but we'll be talking about some of those topics today. We'll be talking about some of the building blocks of them for on here. But yeah, so one of the things that we're going to start off with today is your good old long lost friend. That was the wrong left screen, supposed to be over there. Oh no, my channel cards. All right, I'm gonna have to fix my somehow my screens got mixed up. So all right, we're gonna have to do this some way. Let me see if I can make a new scene, because I need my other. I don't even have a screen for it. Somehow my scenes have been messed up, so let me add in a little channel here real quick, see if I can do it. I need my window capture. Okay. And I want to do that one. Looks good. Okay, capture cursor. All right, so hopefully y'all can see that. This is our good buddy starter, right? And then y'all want to see my face? Y'all want to see my face? So let's put another little image here, and it's gonna need to be, yeah. For some reason, it's been so long. All of my stuff isn't working. Somehow my monitors got flipped. So HD video capture, that should be it. And well, we're gonna have to do. Hold on. May have to bear with me for a moment. And we're gonna do this real quick. And sorry for all this. I didn't realize that this had gotten messed up somehow. Somehow we got these messed up. So Let me do this. See if this helps. It's probably gonna hurt, but let's see. We're gonna do this. Sorry for all of this. Normally this comes up and it just works because I've set it up many times, but I don't know why. Don't know why it's not working today. So I'm gonna have to go through and edit this out, apparently. Hopefully this now works. Let's see. Does not look like it did. Huh. So I'm gonna have to do all this in different order today. Let me get starter up on this other screen. So this is gonna be interesting. Nope, it fixed it. All right. All right, we have starter, and my face is in the wrong place. But we're gonna swing this through here, put that up there where it's supposed to be, and we're gonna get started. Finally, this is what happens. This is why you never go out of town, because your screens get messed up. But we're gonna be doing some work at starter, and the reason we did this is because I kind of realized. Starter A is a little bit lighter weight than installing a full feature version of Portal, and there's a lot of people that use Starter. And Starter can do a lot of stuff, even in sinumeric, that kind of opens up a lot of tuning options and everything. But one of the questions in the help desk was that to kind of go through and see how to set up a S120 system from scratch in starter. And it's pretty simple, honestly. It's pretty quick too. And so we're just gonna, the first thing we're gonna do is just go through and set up a S120 system in starter. So we're gonna create a new project, and I'm gonna name this help desk live. And we're gonna go through, and the first thing we do is we're going to insert a single drive unit. And in a case of an S120, we can select them up here. And in the case of an S120, we're going to be using our C320-2. If you have a different version, then obviously you're going to use that version. But we're going to go through the C320-2, Profinet, our version, our IP address for our online access. Doesn't really matter, because I'll show you the tool we'll actually use in order to connect to it, but we're going to do all this offline. Which, by the way, I know a lot of y'all have been requesting that it kind of use some demo equipment. Hopefully, I just went by a space today that we're looking at renting out and leasing out for Alpha that will allow us to do that. It's here actually in Atlanta, and I'll be able to set up kind of a studio and set up some of this equipment up there to be able to demonstrate it live, because right now I'm in the spare bedroom of my apartment and I cannot put industrial equipment in that. My wife would kill me. So stay tuned for that, and hopefully we'll be able to have a little bit more actual connections and live content, and me using PLCs and actually connecting up to them, instead of just doing everything offline that we traditionally do. So the first thing we've done, we have our S120 C320-2. So if you rename right here, this is the actual drive unit number. And so this is what the control unit name will be in the Profinet. Just by the way, so like drive 1 CU, we might want to name it that. So or whatever. So the next thing you'll do is, if you have a active line module, smart line module, something like that, you will want to go through and do this. And yep, and go ahead and just name it. Let's just throw an ALM here. Drive objects type is an active in feed. Now we have some like technology packages that we'll talk about later, but don't have any right now installed in my version of starter. So go through, Here you'll actually pick your version. I actually have one of these little 16 kWs in my shop, and so I may use this project later. And so pick your 7TE 6A. Next, you want to do a line DC link activation if you're using an ALM. You want to put 480 in. I will say, if you put 480 in here, then it's going to cause some issues kind of turning on the actual active mode. So even if you're on a 480 volt system, put 460 in here. So here in the US, 460, and all this stuff is kind of what we're doing here. Now, on an active line module, maybe I shouldn't do an active line module for this, because we can also put in a braking module external here. So that's what we will have there. Also, we had a question before about what's kind of the purpose of a voltage sensing module. What's up, Ali Reza? I almost didn't see you. I've got, like, my little chat is a little too small. Hold on. Ali Reza, you are avoiding sleeping again in order to watch this. I love the dedication. So we had a question about the voltage sensing module, and essentially what it does is it is an actual device that goes on the actual line side of the device. So it is connected on the line side before the active interface module. So one thing about the active line module is, we talked about this in it, so I won't go over too much of it here, but it's in essence a VFD turned around backwards, pointed at your line. So if you're familiar with VFDs, you know that if you did that normally, it would cause a lot of trouble on your line. It would just, that connection, the pulsing and all of that stuff would cause a lot of problems. So in order to prevent those problems, there's what is called an active interface module, AIM, and that takes care of all of the harmonics, the problems for that, and actually creates a really good waveform. So good that you can actually create a grid certified grid, so like an island grid, or connect it up as like a utility with these active interface modules and active line modules. All that to say is, in order for the active line module to sync up its active capabilities, it needs to really have a good understanding of what's going on with the line. And so that's what, on these larger systems, they have a voltage sensing module that is built into the active interface module, and it's connected on the line side before the filter. And so it's looking at what the line is actually seeing. So it can detect a lot of voltage variances and all of that. These active line modules are a buck boost converter, so they will actually boost the voltage up on the DC link, and so they need to know when to fire, when to phase, and do all of their black magic. So that's what the voltage sensing module is for, and it is on the line side. If you're using an external voltage sensing module, you would click it here, and you would again connect it in the same place on the line side, of the active interface module. So we would normally use like a 370 telegram, just a 1-1, just to control that. And we've talked about that. There is a video out about that. So I'm just going to, you see our ALM, I named it. And so we save this. So the next thing that we're going to do is go to our drives. We're going to insert our drive, and we're just going to do drive 1. And again, here is where you're going to pick whether or not you're going to be using a servo or a vector drive. And in starter, it will actually not let you mix and match drives. So what you want to do for our application, we'll just use servo. But if you want to use a vector axis, like you want to set it up for an asynchronous motor, you would want to use vector, possibly. But servo, remember, servo control does not mean servo motor. Yes, you have to use servo control on this, but you can use servo control on an induction motor, because a servo control just means I'm taking the encoder signal and closing the control loop with the encoder signal instead of the vector calculation. Now, you can't do a vector on that motor, so you have to use servo control. So we're just going to use servo control. Again, I don't have any technology packages installed in my version, this install a starter, but technology packages can be things like cogging torque compensation. If you have like a large like rack and pinion, it will go through and hit the different phases of like the steps. That's cogging torque. There's cogging torque compensation modules. There is actual motion control gearing that you can install on a CU320-2, and so you don't even need a processor to do electronic, or you don't need a PLC to do electronic gearing. It's a little complicated, but that'd be a technology package. That package is called GMC gearing, so general motion control gearing, and it's a free package actually. Like I said, it's just a little complicated. So we're just going to bring this one drive in, and it's going to immediately bring up what is called the drive dataset configuration, so DDS wizard. And we will say, all right, we want to do speed control with encoder. We only have 3 options because we have servo control. We can either do it with encoder, without encoder, or just do torque control. Not really going into that much, but so we're going to do with encoder. Here we could turn on some function modules like our extended set point channel, our basic positioner. This would be what's called EPOS, if you've ever heard of that. If you turn on basic positioner here, you're going to have to use a Telegram 111, Telegram 112. So it's special EPOS telegrams. So we're going to turn that off though. We're just going to click through to set these up. So let's just put in a D style 9 amp. So this is a new motor module. And so remember, the S120 setup has separate rectifiers and then motor modules, inverter bridges. And so we're just going to set up one of these. And I'm in the US, so I want to use NEMA motor units because all of my motor data will need to be in like foot pounds and all of that stuff, and yeah, whatever. So here's where if you have an induction motor or like an ABB motor or Baldor, which I guess those are the same thing, Fanuc, actually, yes, Fanuc motors are different. Kuka uses Siemens motors though. If you had motor data, you could select here and enter the data. But what I'm going to do is just say like a 1FK7 servo motor that has a drive click port on it. That's what I'm going to just say, so that the machine thinks that it'll go through and pull it in. This one, I'm just going to say it's a drive click, and then I'm going to go through no holding break. Here's where you would set it up. The encoder, because it's a drive click encoder, the first time it turns on, it'll go out, look at it, and then pull it in. And so that's what this is. And so for this, let's just pick a I don't know, let's just do like a 103 telegram. You can obviously go back and change that, but that is where you can set it up initially. So we'll go through, save this. I'm going to insert a second drive, servo control. Remember, we need them to be all servo axes on one axis or one control unit. All vector axes will be on a different control unit. So let's go through, and what I want to do for this one, instead of having a drive click, I'll just select a standard motor from list, and let's say a 1PH8 motor, and let's just pick one that doesn't have a, just pick something random. So we have a 9 amp motor module, right? So we need something that has less than 9 amps. That looks like a weird part number. I'm wanting like a M something, M0. That's a 103 though. So if you notice, so this order number, the way that these, the shaft heights on these motors go from like 80. I may have to go back to my power unit and give a bigger power unit. Let's do an 18 amp continuous. So that I can go down and pick like one of these that I know isn't a weird motor. So that's rated. So those are spindle motors. So here's something that's a reasonable spindle. So like this G0 rated speed 2300. That seems like something that's normal. So let's just pick that. Hopefully, we'll just do standard bearing. Okay. Hopefully this has... All right. So here is where we pick our encoder type. So this is going to be coming in on an SMC module because we know, so this will be, oh, that is a terrible encoder. So sine, cosine, incremental with CD tracks 2048. So that's a decent, there's the M. That's the M I was looking for. That's what we use on our incremental encoders. So what this will do is this encoder will actually come in on up here, the signal module. It'll be signal module 1. So I'll just rename this. So as we're going through, increment encoder 1 SMC. We'll call it that, even though that might be too long, but let's give this a 103 telegram as well. Okay. And we're finished. Now, I will say, when we go through and actually download this drive 2, well, no, we actually set it up. So we have these two motors, right? And one of them, we can go through and look at the configuration on both of them. So underneath drive 2 configuration, we have our 18 amp module, and then we'll do drive 1. We have our 9 amp module. Okay. One of the questions that was brought up in doing this, we're pretty much at this point set up in terms of like our encoders. So we have our drive click is going to be read in the first time we power this thing up. And then we go to the other configuration down here and we see that the encoder is up here. Incremental encoder that's going to be evaluated through this SMC module. Okay, so component number SMX is X, and so is 8, and it's a rotary 2048 pulse with 2 tracks. And we're actually going to talk about what all of this crap means, because another question that we were talking in the help desk was about hand wheels and how to integrate a hand wheel into your system. If you're not familiar with what a hand wheel is, it is a little device that's mostly used in machine tool, but it has like a little turning knob on it, and you can, it's intended to when you spin that knob that you move an axis. And so again, it's built-in function into a lot of machine tool equipment when you want to dial in and jog in an axis, to where you're trying to, like, you have a part, you have like a part sitting here and you're trying to jog in your tool to where it just barely touches it. You want to use a hand wheel. And so you'll kind of move this hand wheel. Well, it's actually an encoder. And so you're just moving an encoder. It's just, so in order to integrate those into your system, you need to know what this sort of stuff is. And so we're going to talk about that here in a minute. But what I wanted to show you with this is we have 2 different motor modules. One is a 9 amp, one is an 18 amp. And I wanted to go through and show you a thing called the topology, because it's very important in these systems. So the topology is how the drive system is expecting things to be connected. And what can happen is if you mix things up, depending on how you have a couple of settings, either the system will not work or the system will work unexpectedly, because this topology is like, okay, this is the only way that your system knows, okay, the thing that is connected to this port is supposed to be controlling this motor, right? And so this motor has an encoder on it that's coming back into this module. And so I'll show you what I mean by that. So this is drive to power unit. And the way you kind of read through this topology is on the top of these devices, there's these little RJ45 Ethernet looking switches they're called drive click. So Ali Reza says Siemens has finally released a new version of Simotion Scout for TIA Portal V19 V56 SP1. And he says, of course, with a few days delay. Yeah, I mean, how long have they been saying that they're going to release that? I mean, a few days, like 380 days, 300 and 200 days, something like that. Yeah. Yeah, they're about to come out with, like, version 20 is supposed to be coming out this year. So, yeah. And I'm sure that all of the features that they promised are going to be in that, Ali Raza. It's 100%. So, wow. Don't get me distracted talking about Simotion. You really want me to do Simotion, don't you? I see you. You're wanting me to do Simotion. I get it. But so for those of you who don't know, Simotion is the drives, like, motion platform for Siemens that does, like, you can do very intense gearing and coordination applications. So like printing presses and things like that are normally done with Simotion. It is a very powerful platform. I have a little bit of experience with it, but it's probably been 6 or 7 years since I've done a project with it. And so, like, actually from scratch done a project. But yeah, it's a really cool package, but it's kind of its own thing. And so in Siemens, you have these different development groups inside Siemens AG. And so you'll have the Portal group that's developing Portal, and then you'll have, like, the drives group that develops Starter, and then you have, like, all these other groups, Sinumeric group, the Cranes group, and they have all of their engineers that are developing. Because if you're not aware, Siemens is the world's largest automation company. And for those of you in like basically anywhere but the US, you're like, duh, doesn't everybody know that? But in the US, it's like, oh, wait, Siemens is the largest? Because we have another company that shall remain unnamed. No, I'm joking. It's Allen Bradley. So Allen Bradley is top dog in the US for sure. And so I'm the weird guy in the US that is preaching Siemens. But anyway, all that to say, let's get back. Thank you for distracting me, Ali Raza. So we're talking about how this topology works. So this drive click connections going across the top of these drives are the way that communicates back to the control unit. So it starts at the control unit here, and the way you read this is port 0 goes to port and you that is correct. So port 0 connects to port 0 on the line supply. So kind of the way it's thinking is you're going to go control unit, and then you're going to have your line supply next to it, and then you're going to have, looks like your drive 1 and then drive 2. So it just kind of goes alongside of that. Well, so out of the control unit, port 0 to port 0, and then out of the ALM supply, port 1 goes to port 0 of drive unit 1. So you kind of back it up. And then out of port 1 of this drive unit 1, so port 1 goes to drive unit 2, port 0. So that's topology. Now, if you also notice here, underneath this power unit 2, actually, the way that it looks like this is from, so you have 0, 1, 2. So off of drive unit 1, you have this drive 1 motor, right? So that is the actual connection coming into port 2. So that'll be your green drive click cable going out to that 1FK7 motor that is out there. Well, on drive unit 2, the way that it's connected up is it says from port 2 on drive unit 2, it goes to our incremental encoder SMC module. So now you see why I named it, so it's kind of like easier to see. This here will show up as an SMI, so a signal module integrated controller. Now, why am I talking about all this? One, it's really important to understand how to connect these things up. And the first problem that you'll run across if your system isn't working as it should is gonna be probably this topology isn't set correct. And it'll give you like errors of like, hey, topology error down here when you compile it, or when you go online, it'll say, hey, these things aren't connected right. Even though it doesn't say that. It says topology error something, blah, whatever it is. But if you see topology, go to the screen, and when you're online, which again, unfortunately, I can't do that in my apartment, but when you're online, you can actually look at the specified versus the actual, and the actual will be up here on this, like right above me here in this right hand screen, and it will be shown as what is actually hooked up. And so you can sit there and go through and in real time swap the stuff up. And so you can swap it up, and then down here click this update topology, and it'll go out and look at it. And then you're trying to make your project set match you're trying to make your actual match your specified or what's actually on there. So project set is what's in your project. Specified is what is actually downloaded to the processor. Those are two different things. And one of the things about these Dynamics drives is you actually have 3 different memory areas that you're having to handle. You have your project, your offline project that we're working with right now. You have what's loaded onto your control unit. And if it's straight out of the box, there's nothing there. It's just a default configuration. If it's not straight out of the box, then obviously there's going to be something there. Your project file and what's loaded onto your drive and running on your drive are 2 different things. Then you actually have a third memory area called ROM, which is the storage area of the compact flash card on an S120. So that is every time you start up a CU320-2, it loads whatever's on the compact flash card into memory. And you would think that when you're online down here, because this got loaded up into here and this is running, and you would think that you're down here programming this. You're not. You're programming this up here. You're changing the RAM. You're changing what is running on the processor. And then you have this third, which is over here, that is that's the actual project. So I always say this: if you like what you have, copy RAM to ROM, upload and save. Like over and over and over again. Every time that I teach an in-person class, I will repeat copy RAM to ROM, upload, save. Copy RAM to ROM, upload, save. And I'll say it at random times, because if you don't copy RAM to ROM, all of your changes will get overwritten in the next time it's power cycled, because you didn't take what's running. You're changing. When you're online, you're changing what's running, and you didn't shove it down into what's going to be loaded on startup, which is called ROM. So all that to say, project set and what is specified are 2 different things. The project set is in your project. Woohoo, this is brilliant. But specified is actually what's loaded onto the processor. And so just remember, like, you might have a project set and it matches your actual, but you're still getting faults, because what's in your project isn't necessarily what's on the control unit. So you would have to do a download in order to do that. But what's up? What's up, everyone? It's great to see everybody. It's also great to see members coming in and being able to be on live. I appreciate all the members. If you didn't know, if you're watching this on demand, we do have memberships available, and what you get as a member is here in a little while we're going to be doing a couple of different projects. So we're going to make some PLC data types, and we're going to modify some data blocks, and the members get access to those files. So there's two levels. There's the supporter level, which gets, if I make a data type or something, you get access to that. You also get all the documents. I upload them into the Google Drive. And then there's what's called a programmer level, and you actually get the project archives of what I do here. So today, I mean, I don't know if you actually want this unit here, but I will have a project archive of this starter archive in the programmer level Google Drive, and you get access to everything every month that we do on the channel. So appreciate the members. If you are wanting to support that way, that is what you get for it. But I'm trying to get all of the questions, and so we have gone through, and now we have talked about the topology and the differences of the topology. And one of the questions that we had about swapping and changing out the that just seems a little loud. It's changing out a motor module, okay? And would you be able to change out a motor module with a different size motor module without having to do a download? And the question is, you sound like, well, of course not. It's a different size. But actually, there is a way to do it. So obviously, if your motor is using, say, 10 amps, he just wanted a specific topic about, like, we answered the questions, but he just wanted to discuss online, and that's what we're discussing now, because some of these topics came up. I was actually asked about this in the Siemens training class that we had about this same concept. So if you have a motor that is using, in our example, 10 amps continuous, okay? Well, let's say you have a motor that is using 8 amps, because we have a 9 amp motor module and an 18 amp motor module. So that 8 amps of so that 8 amps is being used basically continuous. So you need to have at least 8 amps of power no matter what. So logically, you would say, oh, if I put in an 18 amp motor module in replace of my 9 amp, I know that I'm going to be able to cover that difference, right? And so you say, okay, this system, I only need to stock one spare, right? The 18 amp motor module, because the 18 amp, if the 9 amp goes out, I can cover it, and then I can cover my 18 amp with that. And that's 100% true. Well, over here, you have this what's called comparison level. And at high, it is actually comparing it to the type. So let's go through and click here, and then click. So I clicked the little icon, and I want to show the comparison level. Okay. At high, it is comparing to the component type, article number, manufacturer, serial number, and hardware version. So when you go out and you go through, everything has to match. So you cannot swap out a motor module without accepting that in some way. So normally, this medium is what you would want to use at minimum. Because if you wanted to swap out a like for like, it would be the same article number. So that would be like this, the 27, let's see. Let's go here. So this would be like a TE21. It would only allow this to be swapped out with a TE21. Or sorry, a 21, in this case, 21.0. It would not be happy if you put a 21.8 in there because the article numbers are different. And this one is even, it has the continuous mark on it as well. So, that medium is what you normally would do. So if you're setting this up, by default, you would want to go down and say medium, because most of the time you want to be able to just swap these motor modules out like for like. Well, if we put this to low, let's see what that gives us. Low says it's the same component type. Okay? So that means that, yeah, so AliRes is, so you're talking about the time for a drive to rise in the mode program with, is a little less than the mode programmed with some motion under TIA. Oh. Yeah, so, yeah, so the concept of the high, medium, and low, the high comparison is, this is how stringent or how picky will this comparison be. So if I were to have this drive 2, if we look at it, what's up, Ignatius? It's good to see you. Good to see you on stream again. So if we have this drive 2, it is a 1TE21.8. So that is an 18 amp motor module. If we have a topology comparison of high, if we wanted to replace this drive unit, we would have to go in and connect up with starter and accept the fact that that is a different module, because the topology will not be happy unless it has the same serial number. So the topology will give you a fault if you don't have the same serial number if it's on high. And it's a pretty simple process to be able to accept it in. There's a place to where you can just click accept. But you have to go in and connect up with your laptop or your PG and do it. So if you have a maintenance guy at 2 o'clock in the morning that doesn't know how to use a laptop, they're going to be calling you in order to connect up to your laptop and say, hey, I need to load this in. That's with a high comparison. With a medium comparison, so if we were to say medium, this drive unit 2, as long as the component type and article number are the same. So as long as it's the same type and the same like 6SL 3120, I think, on this one. So we go to drive unit 2. So 6SL 3120 1TE21 8AC. As long as it is that same order number, then you will be able to replace it. You can disconnect the drive click, swap it out. It has to be the exact same motor module. You can plug everything back up, power back up. You will not have a topology error. Okay, so that's a medium. Medium, it has to be the same order number. So it has to be the same part number. Well, the thing about it is if you take this to low, it takes away the restriction of article number. So it is only looking at the component type. And so it is saying, all right, in my topology, I have a type of a power unit. Okay? So I have a power unit type. It is called drive 2. So as long as I am replacing, as long as the object I connect in is a power unit, it will be okay. The topology will be okay. All right? Now, there's a big asterisk on that, because like we talked about before, moving up to a larger motor module, perfectly fine. So the moving from a small, so like a 9 amp to an 18 amp, and you're replacing that 9 amp with an 18 amp, you're good to go, because it's a power unit. You have set your comparison level to low, and you have connected up a power unit into from port 1 from power unit 1, or from drive 1. Sorry. Yeah. So from 1 on drive unit 1 to 0 on this new power unit. It's connected. It's a power unit. The topology is low, and so it's good to go, because your motor is only going to put out 8 amps, remember? And so now that 18 amps is perfectly fine. All right, so yeah, so Ali Reza has a pretty good question there, talking about the drive click encoder. So drive click, if you've ever taken one of those encoders apart, there is a little board inside of it that actually has a small chip on it that is the actual drive click kind of configuration. And as long as you swap that out, it will say that it is the same object. So there's a couple of different boards in the in that. Normally it's the actual encoder board and not the drive click board that is burned up. And so there's a little header pin when you take off your drive click encoder. There's a little board that has just one little configuration chip on it, and that has the drive click configuration on it that you can plug back into your new encoder, and it has a chance of working out. So in terms of the difference between, if you want to possibly replace a, let me put this on a different screen. Let me get my pin up, because this is kind of an interesting topic to talk about, because it's not always straightforward. So the comparison level, this comparison level is part of your it is part of your actual project file. And so this is a parameter in the CU. And so if you don't have the project file and you want to know what this comparison level is, there's a parameter in the control unit. Right. So this P9906, so this P9906 is the topology comparison, all components comparison level. And so that by default is set high. And so, right. So you can just go into the control unit and look up this parameter 9906, and it will tell you what this comparison level is set to. So by default, it is high, which means you cannot just take an S120 system, unplug it, take out your burnt up motor module, unplug it, take it out, put the new one in, plug it back into the same port, you have to go back on and re-download. So it has to update that the serial number if this is set to high. If it's set to medium, like that, then as long as I'm replacing an 18 amp motor module with the same part number with an 18 amp motor module, then you can plug it in, you unplug it, take it out, replace it, plug it back in. So that's medium. Yes, so if it's set to high, everything, you have to connect up a laptop if it's set to high in order to replace a module. And so I always suggest at most setting this to medium. Now, if you're doing safety, you have to acknowledge the hardware replacement anyway, because safety has different things. If you're not doing integrated safety, then medium makes it to where if I have an 18 amp module on my shelf and I'm replacing it with the 18 amp module, which in our case is drive 2. If I replace drive 2 with an 18 amp module, then you can replace this. With drive 1, however, even though my 18 amp module on my shelf is plenty big enough to run that 9 amp motor, when I plug it in to replace that 9 amp motor module and I plug the topology up, it'll say topology error and it won't let you run because it's set to medium. So project having safety project, or there'll be a restriction. So you can change it to low, and you will have to download it. And so you have to have the project in order to download into the low. And you're not going to be changing any of the safety configuration. But what will happen is when you change that module out, you will have to go into the functions integrated safety portion. Yep. There you go, Lucid. Yeah. So, okay. So this safety checksum will be different. And so I don't have it because I'm not online, but there's some buttons down at the bottom of this screen that will be here. And one of them will be, if you change out a piece of hardware, then, yes, this will definitely save you, Lucid. And so this, if you're using safety and you change anything out, these safety checksums will be different. And so you will have to, there will be a button when you go online that says accept hardware replacement, and you'll have to click that button. And so no matter what, if you have safety, then you have to click, you have to go into this and accept a hardware change no matter what. Yeah, acknowledge hardware. Mm-hmm. Oh goodness. Yes, Alireza, have good luck. Good luck. Type F in chat for Alireza as he goes to bring his plant back up and running. Yes. The button, I'm offline. Yeah, so what? That's like 10 minutes from now. I plan on that because hopefully I can survive like 5 more hours. So yes, the question is the button will be there when there's a hardware change. So it detects the fact it's like, oh hey, there's been a change in hardware. This checksum has changed, and so that button will absolutely be there. You have to click that no matter what with the safety, and so with the safety, the topology going back to the topology level, and for low, if you set it to low, the topology will be okay if you're replacing a motor module with a motor module of any size. So you can go, like in our example, the 18 amp module is for sure going to be able to cover the 9 amp motor module. But what if you had a 6 amp motor module on your shelf? Well, with the topology low, it absolutely would let you do it. And the thing about it is, the only thing that might come into a problem is if your motor's current limit, which I can show you, like here, right here maybe. Yeah, here. So if this current limit is higher than the actual capacity maximum power unit output current, okay? So it will automatically limit the output to your motor in order to protect this maximum power unit output current, right? So it will automatically limit the motor output. Well, guess what? That might not be enough to run your load. And so, with that low topology level, it will just let you do it, and then you might start getting other faults, like a 7900 motor blocked fault, 7902 motor stalled fault, these sorts of things. And so those, awesome, LFC. So LFC, thank you. I hope you've watched the first part. LFC 27 is one of the ones that was awesome in help desk this week, helping each other out. And so, yeah, if you're just joining in, we've been live for a little while. So if you're just joining in, this content is all about from tales from the help desk. So just questions that have come up in the Discord server. If you're interested in joining the conversation in the Discord server, the link is in the description below. But yeah, so kind of talking about this low level of the trouble. Well, anytime you're trying to help people, that's awesome. So we really appreciate the community trying to help each other out. So yeah, so we're talking about kind of the trouble that this low comparison level can get you into. So it will let you put in a 3 amp motor module for a 9 amp as a replacement. Now, your process might be okay with that. Maybe you've oversized that process. Maybe that motor's actually too big. Maybe it's just like, and like you're able to do that, and it would be able to run. And so this low topology is only required if you were wanting. I probably would not put this in by default. So like, in what I would do is, if there was a situation to where you were like, we don't have a spare 9 amp motor module, but we have a spare 6 amp motor module, and you're like, okay, we've looked at it, I think we can get by with using the 6 amp motor module. Well, at that point, take it from your default medium, say, okay, I'm the engineer, I'm going to make this decision. I've looked at it. I think it can run on the 6 amp motor module. So I'm going to come in, pull this down to low, and then download. And that's the only change you would need to make, is just go into this screen, put low, and then download, and then your topology would clear up. And so I would not put this by default on a piece of equipment, because what may happen is you might have a maintenance worker that goes out, and maybe you have a 9 amp and an 18 amp, and they're the same they're the same physical size. And they just go out and look, oh, part number's TE21, and they don't realize that that's TE21-8 is an 18 amp, and TE21-0 is a 9 amp. So they go and they think that they're putting in, they're putting in an 18 amp, and they put in a 19 or a 9 amp. And if you have that set to low, then it'll be perfectly fine. But then you might actually mess up your process if they just put that in like that. So I normally put that to medium, and then if you have to have a call about that later on, then you'd be like, hey, I don't think you're putting in the right motor module. We have an 18 amp motor module on the shelf. You picked the wrong one. The part numbers aren't the same. And so at that point, they'll go to the shelf and they're like, oh, I see, this is a -0 and I need a -8. So hopefully that's a good explanation of the medium level on this. And so we will go from there. So we're going to go through, I think, I'm going to check. We're going to spin through here. And what was, I think you asked a question about, let's see. All of the questions were, hopefully, I think I remember them being about the, I thought I had them written down. But I know one of them was about the pole ID function. And I wanted to talk about kind of motor encoders, and we had someone that also asked about replacing a motor encoder and kind of like getting into the insides of these encoders, because it's kind of crazy. Like, especially in the US, most of the time they just take the whole encoder off and just toss it, and you realize that, all right, you probably can actually replace this encoder. One thing about Siemens motors, so they have what are called Generation 2 motors, and they actually have keyed shafts to where that if you replace an absolute encoder, you're going to have a single turn. Let me get this going in the right thing, and then bring this down here. Let's go to here for a second. We're going to talk for a second about kind of like what absolute versus kind of these other types of encoders, because you need to kind of understand about, all right, so I'm kind of covered up, but I got the sketch pad down here, and what we're going to be talking about is for this, an encoder is just a way for, if we have a shaft, or in this case we're going to talk about the motor shaft, to get what our actual position is in whatever degrees. And so if this is 0, we'll say this is 45 degrees, okay? And the purpose ultimately of an encoder is really just keeping up with that rotation and where this shaft is in relative to yeah, Ignatius. Yeah, so Ignatius, you're exactly right, and that is Ignatius brings up a perfect point, and the one that I was trying to making sure. If you're responsible for a piece of equipment, then you're responsible for the safety of that piece of equipment. You're responsible for the hola, Hola. You're responsible for the proper operation of it. And as an engineer, you need to kind of like take pride in the fact that like, okay, this is my equipment that I'm responsible for. And other people, you can't assume that other people are going to take that same responsibility. And like in my example, with, say for example, you set this is on a crane system or some sort of hoisting system, and you're you have an oversized module, and you've set this comparison level to low, and a maintenance worker at 3 o'clock in the morning goes out and swaps out accidentally that 9 amp motor module, and it's on a crane system, okay, and that crane goes and you're like, oh, all right, cool, it worked, sweet, we got it back and going. I don't have to call Ignatius or Jason or you. I don't have to call them because it's working. And next thing you know, they go and they lift up a load, and it lifts up and works fine, but then all of a sudden it overheats and faults out, and your brake slips and it falls and injures, possibly kills someone. And so that is kind of like a very dramatic thing. But guess what? Like, should the guy have been more careful? Yeah. Was it an honest mistake? Yeah. Was it a pretty easy mistake to make? Yeah. If you notice, that part number is only one number off, and it's an 8 and a 0. So if you're like maintenance worker just kind of just doesn't even like really look right, an 8 and a 0 kind of looks the same. And you're setting it up to where, hey, guess what? Someone could get hurt. So I agree with Ignatian there. There's a lot of wisdom there in things that have a possibility for having those sorts of mistakes. Just, I'm going to make those. And I'm going to make those like decisions because I know I'm going to check them. And I feel like you should do that as well. And honestly, if you're looking to not necessarily impress, but make an impression on owners, people that take responsibility for their work, engineers that take ownership for the things that they design, whether it be in just accepting mistakes, accepting responsibility, those are the ones that I want working for my company. And those are company owners. As engineers, it would be like, hopefully you don't make mistakes. But if you do, you can say, no, that definitely was mine. I should not have done that. And as an owner of a company, if an engineer does that for me and says, oh yeah, I messed up on that, it doesn't really like, especially if someone's injured because of it, it doesn't like change the situation, but it makes me want to work with you better. And it makes me want to kind of be like, hey, I know that this is an engineer that I want on my team. Even though everyone makes mistakes, this is an engineer that takes ownership. And so Ignatius, that's a wonderful, wonderful thing for you to do. So we're talking about these encoders now, and I get distracted. Obviously, the things I have a passion about, I get distracted about. And that is one thing that I really have a passion about, just in any young engineer coming up. You don't have to know everything. You're going to make mistakes. And if you are working for someone that punishes you for taking ownership, you don't want to work with them. Sorry. You don't want to work for an owner, a manager, anyone. And I say this as an owner and a manager. You do not want to work for people that does not at least appreciate the fact that you take ownership. Now, if you make a mistake that costs someone their life, hopefully you understand how impactful that is. And so when you're going into engineering, you need to be humble. You need to understand that this is not, oh, I put a wrong number into my Python program and my Raspberry Pi light came on at the wrong time. This is something that could literally cost someone their life. So be humble, take ownership, and take yeah, take responsibility for it. And I think everybody in here on these chats and in watching these videos already have that, because you're taking your time, you're taking your optional thing. You could be doing something else. You could be, but you're taking the time to learn. So it's probably not talking for you. So hopefully you take that as a word of encouragement in the way that you already operate. Let's get back to these encoders, because there's a couple of themes in both of these. So one of the things about this encoder is the fact that reminded me to keep the pointer. It doesn't show the pointer. Why does it not show the pointer? I think I know. Hold on. I think I know what's going on. one of the comments from one of the members was trying to yep, I figured it out. I did not capture the cursor on this screen. Look at this. You can see what I'm pointing to. And you can even see the little pencil now. I fixed it. We fixed it, chat. We fixed it. Now my drawing tablet, it shows my pointer. So, oh, little victories every day. So an encoder is ultimately only keeping up with 360 degrees. Now you say, Jason, a multi-turn absolute encoder keeps up with much more than 360 degrees. And you're like, yeah, okay, you're technically right. But all it's doing is keeping up with one rotation and then keeping up with the number of rotations. So it's keeping up with the degrees, and then it says degrees times 1, 2, 3, ... So one of these things about in motor encoders is, especially like in an absolute, so you have incremental, absolute, and then you have absolute multi-turn. Okay, so these are the three main types, and you have things like resolvers and stuff too, but we're going to talk about just encoders for right now. Resolvers are a little bit different, but in incremental, you have pulses as you turn, as you move, and so if you don't move, you don't get pulses. Absolute encoders, if you don't move, it still knows where you are, because it has a little physical disc in it that has like slots in it that keeps up with where you actually are. So that's an absolute. Absolute and absolute multi-turn are the same, except you have this number of counts, number of rotations. So most of the time you'll have a pretty accurate like 4098 pulses. So 4098, so 360 degrees divided by 4098. That's kind of like your single turn absolute. So that's, and then you'll have like an additional number of multi-turn rotations, and then that is just, so if you had another 4098, for example, that would be times 4,900 or 4,098 turns. So single turn accuracy, and then times how many rotations you've made. So that's what a multi-turn is. Now, obviously, there is a lot more. There's things called load tracking. So even if you exceed 4098 turns, you still keep up with your position. Like there's all sorts of stuff that happens to be able to keep up. And there's even inside your 4098 of your single turn, there's a fine resolution to where it can see the changes in the motor, and it knows that it's changing even though there's not a change in the encoder. So it will actually kind of interpolate in between pulses. It'll interpolate between points in an absolute encoder. So really a lot of accuracy encoders, but ultimately it comes down to keeping up with a degrees. And there's two ways to keep up with that degree. So with your degrees, we have that. With an absolute, I said there's actually a disk that it's looking at. So there's like an optical disk that it will encode in the actual position based on how many options there are. And there's a couple of different videos that are out there. We're not really get into that. But one of the reasons that you need to know this position is on a servo motor. Actually, I'm not going to call it servo motor. On a permanent magnet servo motor, so a permanent magnet motor, like this guy. So a permanent magnet motor like this little 1FL6 motor, you have coils of wire on the stator, and then you have permanent magnets on the field or on the rotor. So there's actual magnets glued to this thing. And when you turn it, you can kind of feel it like doop, 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 because it's kind of got, it's like those magnets are aligning with the different stuff inside here. So that makes a permanent magnetic field coming from this rotor. The only way to control this motor is to know the orientation of those magnets, the field, to the orientation of the rotating magnetic field here. I talk about this a little bit in my industrial motors video, and so I'm not going to go into it too much from now. Just know that you have, with an AC, an alternating current waveform, you have a field, a magnetic field, like a magnet pole that is kind of spinning around and rotating because of that, the AC waveform inside of here. So the only way for the magnets in this rotor want to line up with the rotating magnetic field. So the only way for this motor to be controlled is if the drive knows where that position is right there. So if the drive doesn't know where that position is, it doesn't know how to fire the pulses in order to line up that magnetic field in order to move this motor. So rotating magnetic field generated by the drive, permanent magnet field, they have to line up in a certain way. And so one thing, when you buy a motor, this is an absolute motor. Yeah, this is an absolute single turn encoder. 21 bits. So really high resolution. So this, from the factory, this encoder knows its alignment of this. So it knows that this shaft is say at 0, and it knows that the shaft coupling here is also absolute. And so it knows that relationship between the drive. It isn't just sorry, lots of stuff going on. So the drive has what's called an encoder angle offset. So by default, it might be 0, it might be whatever, but from the factory, you know it's already there. So there's a function that if you take off this encoder and replace it, say you take this thing apart and pull it off, you want to try to keep that angle the same, but if you put it back on and all of a sudden the shaft inside this encoder is a little bit off, it's twisted, then that angle between the magnets and the field is going to be off. And so what happens is this drive this drive is not there. So what we can do is we can go through and look at a couple of different variables on this, and I'm going to bring this up so I can see it a little better. Let's go to this one and bring this guy up here. I don't know what I clicked. Oh, I clicked measuring function. So let's go into which one? This one is this. Let's go to the Drive 1 expert list, because there is a motor. I don't know if I can do degrees. So let's sort by angle. And pole position angle. So that is the angle relative to your encoder. And so reference angle is 0. So the question is, what is the actual angle angle of your encoder? So let's go through pole position angle electrically scaled. So that is the R93 is based on the angle of your pole relative to your. I want to make sure I say that right. Go to parameter help. Displays a scale electric. Thank you. For operation code, the following applies is generated from 90 over plus 180. Okay. Let me use. So let's look at this. Transformation angle. Pole position angle is output via test socket to adjust the encoder, determine the test socket's VMSP parameters follow. Yeah, so this is the encoder angle for that encoder angle offset. So let's look up something real quick, because the pole ID, I think, has an explanation of this. If I can find the correct one, because when I was looking at this, I thought that there was one that tells you what it is. So these are so these are not encoders, those are motor values. The saturation base. I don't think this is it. This isn't it. I think it's in one of these. So I did this a long time ago to where I had to actually set up it was a KUKA. It's a KUKA motor, but it was actually a 1FK7 motor. And so let's look at some of these values here. I'm going to pull this down, pull this up here, and in that there is, let's just delete this. And let's go to some of these. So 325, motor pole position identification. Okay, so that's that. 329. Because in there is somewhere where there is an actual pole position. I thought it was that angle. Let me do something real quick, because Bum, ba-da-da-do-do. So what I did, and I'm kind of showing you a couple of techniques for the fact that, like, I'm just looking for an angle. I'm looking for a value that is an angle. So you can go up to the top here and sort by unit degrees. And all I did was just went in and found a unit with degrees and just copied and pasted that into there. Yeah. So one of the things about it is this, if you go through and replace an encoder, and I may have to come back on this because I thought I had done research on this and I apparently have not. So I'm going to have to come back to that particular question. So the actual angle of the encoder, there is a position that is in the, it's called, let me delete these out. It's X. Is that it, or? Yeah, so this isn't it. So, because I don't think I have it enabled. So this XIS. So XIS. Let's do this. Let's see if we can find it. I'm gonna have to come back on that because I mean you have this actual position value here, but that's not going to be in the degree, and I think that there is a way to get the encoder degree out of this, but I don't know which it actually is. The encoder offset is that this angle here, but yeah, so there is a document that is in the member area. See, R93 is the that's the pole position. So that is the electrical pole. and one of the things that the issue is like actually being able to find that thing. So let's look at that document that I put, because I thought that, let's read in it. Let's learn together. Let's look at this document and see what it says. So this is a document that actually goes through and was given to me a few years ago. Trace R89 and R93 of the drive. And so I guess that is what it is. So yeah, so so it's set up R89, which is actual phase voltage, and then pole position angle electrically scaled. Okay, so yeah, so that's what this is. So this procedure is what's called the manual calculation of encoder commutation angle, and I wanted to go through this. And so there is a pole ID function that we kind of went through that is the standard. So this is the angle. So the pole position angle electrically scaled. So enable the mode, and then on this trace, the phase angle of the encoder is not correct. You may see something below, like for this, of course, 20 degrees. So instead of this crossing point being at phase 0, this is the problem. So this yellow line here, which is R93, that is the electrical, or sorry, the encoder position. And so what that encoder position, and that's encoder position for you, as it matters in the motor. So where, see, it says a 0, the 0 volts is the phase angle. And so as you spin that motor by hand, as you take, and again, it has to be enabled, you spin this motor by hand a few times, and then you go through, and it will take the encoder position, that pole position encoder, and if it is not crossing like it shows here, then what will happen is it will look something like this, to where the crossing point, so 0 volts, this 0 volts, it's crossing at the wrong place. So 0 volts, there's a lag. And so this difference where this drops to 0 on the, and crosses over from 360 to 0, that's what this pulse is showing. The yellow line going up 360 and then dropping down to 0. And so where that drops down, that needs to be here. And so the difference, you measure the offset. So measure the difference in degrees, which in this case, let me bring this down onto the other screen because I need to draw it out. The angle that you're needing is this yellow line. Sketchpad. Right. And so let me sketch it out. So we'll scroll up and show that 0, this 0 point and 0 volts is crossing at the same time, at the same point. So R89 is the phase voltage, which we talked about before. In a motor, you have the rotating magnetic field, which is caused essentially by the voltage in the windings. And so that's what matters. So in essence, you can think about R89 as being the firing where it's supposed to be. All right. So where the motor, or I guess where the drive thinks that the electrical 0 is going to be. So 0 volts phase voltage, you should have that at 0, of your pole position should be at 0. So that's what you're trying to align. So don't think about it as the actual encoder position, because you kind of get tripped up, because technically that's not the encoder position, because it's doing some calculations that you don't need to know about. The drive just needs for this to happen. So this is the R93. Yeah, so R93 is what the drive considers the rotor position, the encoder position. And that's what matters, because R93 is what the control system is based off of. And so if R93 isn't in the right place, if it's not crossing in the right place, that's why you have to put this offset in. So let's clear that out. And this does not have an offset. It crosses 0, crosses at exactly. So this is good. All right. That's what a good one looks like. The author of this manual went through and intentionally put an offset into the encoder to show this value. And so here is 0 volts. And you're crossing, there's a gap, right? There's this gap. That's the problem. So what you need to do is you go down and then you measure this angle. So this angle, which I think he said he put it 20 degrees, which if you were to click right here, it would change the scale. It would change this scale over here to scale to the yellow. And that's what you would want to do. And so this is, if you went over and it scaled over, this would be 20 degrees. Does that make sense? And so you would put into P431 would equal 20. Because this yellow line is what the drive is saying the encoder position is. When you slipped it, when you put it on wrong, that number is wrong. And so when you're saying, is that the actual encoder position? It doesn't really matter. That's what the drive thinks is the encoder position. And so that's what matters. And so that's how you put this encoder, this slip in. And yes, Lucid, this is only on one of the older absolute encoders. So like for a what is called Gen 2, they actually have a keyed, they have a slot, like a V groove slot, to where you can only put an encoder on one way. And so this isn't relevant for newer servo motors. So if you replace a Gen 2 1FK7, it has a little cam lobe on it, and so it aligns it itself physically. And so those are kind of like aligned, so you don't have to worry about this. But if you have an older version motor, like a 1FK, like a 1PH7, which I know y'all have them out there, then, and you had absolute encoders on those, or a first generation 1FK7 or 1FT7, like might be on your T-Jacks on line 1, for example, those, if you were to replace that absolute encoder, you might have to do this. So how the drive measures R93, it is getting a signal into a processing area from an onboard chip in that absolute encoder. And so it has a communication back and forth on it. So it's either through SSI or whatever, and it's getting a position that is coming back and saying, I'm at this position, and then the drive is set up for number of turns, number of pulses, number of revolution, and then it is generating this R93. So in a incremental encoder system, let's see if let me look up real quick on this. See if it actually shows in the motor encoder the evaluation. It doesn't show it here. There's a function plan that has it on here. That shows the encoder evaluation. Siemens manuals. And let's do S120 list manual. I'll open down there. Figure this out. And I want to say it's here. Yeah. So this is really in deep. Yes. Yes. So here is the really in deep method, but you don't have to know what this is. Like, you don't have to know how. it takes, so see if we can zoom in here. So it brings it in and provides that value. So in this case, it's bringing in the encoder and then it's providing that value. And so all this stuff, and there's obviously a lot even more, you don't need to know all of that. You just need to know that the oh my gosh, come on, click there. You just need to know that it takes care of that, and that R93 is the angle that it is saying is the actual encoder angle. As far as anything's concerned, that is what you go off of. Awesome. Thank you. We got another member in here supporting the channel. Throwing in a like and comment to get it out here. We're still going to be on for a while. I know we've already been going for 2 hours, but I have some more stuff. Hopefully that is pretty in depth on what I mean, that's really as in depth as it really needs to be on this, because R93 is going to be it's going to be the position of what oh, that's control unit, that's why. It is going to be what you were looking at for that. So maybe that was so you don't really, if there is an offset, you're putting that offset into that that parameter 431. So we'll go down here, 431, angular commutation offset. So that is your angle that aligns up the actual encoder and this value. So yeah, this document will absolutely be in both tiers. So what's up, Worm Bros? It's good to see you on. And if this is your first time on, be sure to drop a comment into chat and just say hey, because we're hanging out, we're learning about drives, we're learning about all sorts of stuff today. But we just went through a pretty in-depth stuff on starter and all sorts of topics, trying to clear up stuff. And just if you're on Discord and yeah, if you have more questions, we're going to cover. I'm going to move on a little bit on to the next thing, because we have quite a few more topics that we're going to talk about, and we've been really in depth in this one. And so, yeah, as we're moving on through this, what was the next thing we wanted to talk about? What was it we were talking about? I think it was, before I get off of talking about the drives, because we talked about absolute encoder adjustment, we talked about motor module swapping. I wanted to talk a little bit about breaking resistor sizing, because this was brought up, and it's brought up actually a good bit. And let me bring up, I don't think, let me go up to this screen for right now, because the breaking sizing, yeah, I'll put all the documents that are on stream, I will put into the member upload areas in both tiers. So again, just a little plug on the memberships. All of the documents that are on any of the streams are going to be in the member area Google Drives, and depending on what level you're at it, you get it. You get different documents. So these will be there after the stream. But we're going to be talking, I want to talk a little bit about breaking resistor sizing, because I had a question about, I've got this breaking resistor, can I swap it out? And one of the things, there's two main features about breaking resistors that you need to kind of understand. The sizing on them are usually in kW or horsepower. Most of the time it's not in amps, because your amps are usually much lower than, because a braking resistor is going to be seeing around 600 to 800 volts. And so it's really, your amperage is actually not very high on that sort of stuff. So I say that it's not very high. It can get pretty high. It's a lot of energy going out, and your braking power is based on power. And we may or may not know that horsepower, or kW, are the units for power. In Siemens drives, there are the braking chopper is set up automatically to regulate on current and output at whatever voltage is being chopped into the circuit. It is going to output the parameterized amount of power. So what power value on a resistor do you use? Because a lot of times the you'll have like all right, this is a 1 kW resistor. Okay, is that 1 kW continuous, or is that 1 kW peak? Don't know. In Siemens braking resistors, they rate them on both. So you will have a continuous rating, which means if you have like I don't know, like a continuous braking process, like an unwinder or something, and you're just wanting to put braking force onto it, that is going to be the amount that that resistor can run S1. So absolute continuous. And usually it is a lot less than the peak, because the peak loads on these braking resistors are usually set on a 600 second total duty cycle, and then a 3-second peak load. So that means you have 10 minutes. Every 10 minutes, you can have 3 seconds of that peak load. Not a lot. And if you do, say, every 1 minute you're hitting that peak load, you're eventually going to burn up that resistor, and it's going to be damaged because you are exceeding that duty cycle. So the way that you do it is you sit and you need to calculate your braking load. If you don't know, then you can kind of like ballpark it on how often are you actually braking, and just say, okay, how often am I braking? How often am I slowing down? And if that is less than 10 minutes, or sorry, more than every 10 minutes, I'm saying that backwards. If it is less than once every 10 minutes, so like if you only ever slow down once a shift, or maybe once an hour, then most likely you will be able to get away with the peak load, or the peak power rating on that resistor. And so just in general, if it takes 10 kW, if you have a 10 kW drive, and when you accelerate, and if you accelerate and go into torque limit, that means that you are exceeding, or you are hitting the peak amount of power that the drive can output. If you have a 10 kW drive, you're probably hitting about 15 kW, roughly. So if you accelerate and you hit 15 kW, you can turn that around and say, if I want to slow down that fast, I'm going to have to brake the same amount of power, or more, if in essence, because when you're accelerating, that is overcoming inertia. When you are braking, you are overcoming the inertia of a moving system. And so when you brake, you are going to be using the same amount of power that it took to accelerate to that speed if you were braking at the same rate. Most of the time, an emergency braking situation though, we are trying to decelerate faster than we normally accelerated. Say we have some sort of roll, or something that's like sped up. We sped it up in 10 seconds because we want to kind of be easy about it. And all right, we are we don't hit the torque limit when we accelerate at 10 seconds, but when we hit an e-stop, we want to output uh, yeah, so we're wanting to output like to say we want to stop it in 3 seconds. Well, the only way that you would be able to actually do that is have the drive be sized for that amount of braking, because if the IGBTs can't handle it, which they can handle like 200% for 3 seconds. So if you have a 10 kW drive, you can brake for essentially 20 kW for 3 seconds. It's just kind of ballpark numbers. But a way that you can kind of test to see if how much current it's going to take and how much power it's going to take in order to actually break that system, you can accelerate it. And you can accelerate it faster. And you can kind of get an idea of how much power it's going to take. And you'll have to overcome friction when you're accelerating. So if you do that calculation and you say, oh, I had to output 10 amps, whatever it is, just making numbers up. If I had to output 10 amps in order to accelerate this at 3 seconds, that means I'm going to have to bring back in 10 amps. So you can do that calculation, and that would be, what, 4.8 kW? Carry the 0, 480, or at least in the US, right? So that'd be 4.8 kW of braking power needed to brake that in 3 seconds, running at that speed. So, yeah, so we kind of have the same for braking resistor. I'm using other brands. Siemens is necessary expensive. Yep. Usually we're choosing the max motor power times 1.5 will cover most of the scenarios. Yeah. In general, the kind of like in talking about the braking resistors, if you were only braking once every, like maybe once a shift, or even like 5 times a shift. So as long as it's more than 10 minutes between braking intervals, then yeah, you can use the peak power and just make sure that it's braking in 3 seconds. And kind of like commenter OG said, he said, so take the power of your motor times 1.5. That's, by the way, the default settings for the current limit on the drives. So kind of the scenario that I was saying about however fast your drive can accelerate it without going into a current limit, that's as fast as you probably want to try and brake on the other side, and that you're not going to be worried about damaging a drive. So second question is, if we use the ALM, we don't need the braking resistor at all. Under normal operation, you are completely correct. So the active line module is what's called a regenerative braking system, or a regenerative drive. And by the way, it's the best one. I did a whole video on the active line module. Y'all should watch it if you want to know about it. But it literally, if you pick an active line module, I say if you can accelerate it, if you can accelerate your load, it can stop that load just as fast. And you don't have to worry about it. The only issue that you run into while using an active line module is you might have a breaker in series. So you have a breaker in front of that drive, right? So if you have that breaker and it's not rated for reverse feed applications, which there are some cheap breakers out there that, like, God forbid that you get a cheap breaker and your current is going through what's called reverse feeding. Some breakers aren't rated for that, and so they will actually open up and get damaged by that. And so if that happens, your active line module doesn't have an anywhere for that energy to go. And so it has to protect itself. And so it'll just shut off. And so that means your load will just freewheel. So the active line module, as long as the line breaker does not open up and there's somewhere for that energy to be taken off to, then it will do it. The only time that you might need a braking resistor is if you need an emergency stop situation on an active line module that has to operate if there is no line connection, if there's no power. And I know you might sit back and be like, well, how in the world can the thing stay up? Well, if you have 24 volts on your system, then you can keep that up. So you can put a UPS system in and keep the 24 volts up. And then if your power browns out, you may not have the ability to dump power back onto that line because you don't know why there's no power there. You don't want to be dumping energy back on the power a line because that's going to be real power. So you would want to instead, if the line dropped off, you would want to disconnect that connection and then break off that braking energy, keep the system running, but start braking. That will generate power for the DC bus, and any extra power that is going off needs to be burned off with a braking resistor. And so only in very very specific applications would you ever need to use a braking resistor on an active line module system. And that's very, very strange, very kind of unique situations that you would need that for. So but yeah, active line module, that's another thing. It's like, if you buy it, for the most part, get a good breaker, get a leading auxiliary contactors on, or contacts on your breaker, hook those in, because if that breaker for some reason opens up, the active line module it'll see that voltage starting to brown out. It doesn't know that, oh, hey, the breaker's open, unless you tell it the breaker's open. So you got to have that, that switch. And so what will happen is it will start, as that voltage starts dropping off from the line being disconnected, it'll actually start phasing stuff forward, and it can damage the drive. It can damage a lot of stuff by phasing everything forward, trying to keep that DC link voltage up. So if you're using an active line module, don't skimp on your breaker. Get the proper stuff. So braking resistor, pretty much, if you want to know how much energy it's going to take to stop your drive system, just try to accelerate it at the same speed and record that current. And then you know how much power, the current times your voltage. So pretty good. So Ignatius says there's a trade-off of going for cheap products, and as long as production increment is required, your motor may be breaking more than you intended. Is it just because someone wants to increase production? Oh, absolutely. Yeah. And that Ignatius brings up a really good point there about the breaker, or not the breaker, but the process causing unexpected braking energy. So there are a lot of different reasons why you would end up putting braking energy back into the system. So like anything with a lot of inertia, you get it running up to speed and you load it down, you're going to pump in energy to get it back up to speed. Well, that energy that you put in may cause a little bit of overshoot in your speed controller. And so in order to pull that back down, there's going to be a little bit of energy that's required to slow that back down. Even if you're running in volts per hertz mode, remember, anytime that your rotor speed exceeds the frequency of your drive, so if you're outputting 50 hertz, 60 hertz, anytime that your rotor speed exceeds 60 hertz or whatever, then it's automatically going to put braking energy back in. So like to Ignatius's point here, that if you're trying to run faster, you might be pushing the machine too hard and it's overshooting that speed, and you have inertia and there's braking energy that's coming back and you don't even realize it. And so if you have a braking resistor, you might have 4 or 5 or like a few hundred watts of power just sitting there, kind of like average, burning off. And then when you go to do a e-stop, you technically might have used up all of your thermal capacity in that resistor, and it's already hot, and you go to do a brake, and then it just opens up because it's already been damaged. Yeah. So Ignatius makes a point. So he puts braking resistors on his ALMs, and I respect that. I respect that greatly because with that, you are ensuring that in the event of an emergency situation, an e-stop situation, that energy is going to have somewhere to go. And I mean, come on, you're spending tens of thousands, if not hundreds of thousands of dollars on these drive systems, and you can keep a drive safe just by putting another, say, $1,000 onto that system. Yeah, that's pretty good insurance. Yep. It says that many of the customers want to reduce the price. Yeah, I mean, if your customers, and this is just from my experience, if your customers are not accounting for engineering hours, their engineering hours, and their budgets are separated to where like their maintenance budgets and their capital budgets are separated, you're going to run into exactly what you're talking about, because there is no way for companies with two different budgets to what's called like amortize in engineering time, and like they don't have a time cost for something. And because a capital expenditure of $3,000 could save $100,000 in maintenance cost, but because it's on the capital budget, they want it minimized. And so so yeah, so we're, it definitely is going in. And so yeah, so yeah, I'm going to make a turkey. Yeah. Oh, hey, it's not just for those places. It's here in the U.S. too, and it's like, yeah, my plants, like my production facilities, I always say if it was my machine, here's how it's going to be. And like in general, that's where I put my money to it. And we have very efficient machines. And the companies that say, hey, we trust you, Jason, we trust you, Alpha, in making those decisions, they're very profitable. So, but yeah, so I'm gonna take a little bit of a break because I've been drinking some water and we've been going for 2 hours. So I'm gonna take a break, go relieve myself, and go ahead and type in your 2 questions. You can absolutely have those. This will take me about 30 seconds to walk in the other room, and yeah, type out those questions and I'll answer those other questions when I get back. All right, told you it was going to be quick. In US, we call that a bio break. Yeah. So, what were your... If we replace the modules or SMC or encoder, or if it's set on the higher level. So, the SMC modules, you're talking about the topology. Probably about the only thing that you would actually be able to get away with and not have to recode things would be if you had a newer version of the same module. Because what's going to happen is you have all these configurations that are set up for a specific type of encoder, and if you like change out your an SMC module, or so here's one thing. So there's what's called an SME, so echo, and then there's an SMC. So it's signal module cabinet, signal module external. Those are two different part numbers, but I could see a time, like if you could swap between those and not have to have a problem with a lower, because otherwise the only reason you would be changing a signal module would be if you were changing changing the type of signal module would be if you were changing the type of encoder, and you're going to have to go through and reset up the hardware. So you will have to go in and say, I have a different type of signal module, I have a different type of encoder, I have these different encoder settings, like you're probably going to change your motor like there's a lot of things if you were changing out an SM module, because the only reason you would change that out is if you were changing a different type. The only exception being if you were going from like an SMC to an SME. Those are two different part numbers, but they're the same function. And so maybe that'd be the only see why you would do that. And that kind of goes back to that. That kind of goes back to the principle of do you really want maintenance people making major changes on a machine? I mean, it's up to you on things like if it's a machine that's not that big of a deal, maybe that could be made. But yeah, you would need to go back into the hardware configuration, because so like you use a SMC 30 for an incremental tracks, you use an SMC 10 for resolvers, and so if you're changing part numbers, you can't use your encoder with an SMC 10. So you can't use like an incremental encoder with an SMC 10 anyway. It just won't work. You put it in and then it'll fault out, and then it'll be faulted anyway. So that's kind of that explanation for that. You said you had another question too. While you're doing this, I'm going to bringing up Portal. And again, I'm going to throw all these. Okay. Means even if only the hardware version is different. If the hardware version is different, you could get away with that. Because when you go through and start up the but that would be, so that would be a low level setting. Actually, no, that would still be a medium. So a hardware difference. It's still going to be the same order number. You could still change it out with a medium, and what it would do is it would go in and see the new hardware version, and it would try to do an update on it, and on like any drive click, it would get to the correct firmware, and it would go from there. So let's go through, and I'll have to remember. Yeah, go to your second question. I'm gonna pull up TIA Portal because we're gonna talk about another application here in a second. Let's see. Yeah. All right, let me get this pulled up here. So we're coming with the second question. I'm going to be pulling up Portal. Oh, and by the way, I kind of missed your OG about the flying saw application. Yes. I'm going to go through the concepts of a flying saw application on Motion 102, because Motion 102 has to deal with kind of advanced synchronized motion, and a flying saw is exactly the application that kind of really details out all of the things that you really need in a motion, like a higher level motion. Because we've already done a thing on kinematics, and kinematics are really high, but a flying saw, definitely I've done them before, and there's a couple of different ways to do them. And yeah, in terms of a motion application, that is going to be it. So, not a fly. So, a rotary shear. Oh, you're talking. So a rotary shear would be, yeah, like a flying saw is a simple one. You got jokes. Yeah, so we're talking about we're about to talk about that synchronization between two chains, because I had a couple of different, or two motors. So there's one company in Turkey that's able to do a flying saw or a rotary shear. Because I mean, flying saw applications are pretty rough. Rotary shears would be, I mean, I'm sorry, they're pretty basic in terms of motion. What horsepower are you talking about? Are you talking about like steel ingot? So you're talking like 1,000 kW, 2,000 kW? What size is the shear? $300 kW. Yeah, that's pretty big. So, to answer your question about what's the best way, so there is a pole ID function, and it will determine the best way based on what motor and encoder you have. And The only issue that you can come into with the pole ID function is if it exceeds, because it will try to rotate. So essentially it's going to go through and move at different phase angle offsets. And so in your case, though, you have two. You're changing one. Oh, okay. I got you. So honestly, I would, for you and your, I see what you're saying. They're tied together with a chain. Here's what, if you change one, so in that document that's going to be in the member drive, it tells you how to set up the motor in order to make it to where you can turn it by hand. Well, what I would do is I would turn the other motor, so use one motor to turn the other. So you would put the one that you're changing, out into what's called a fixed end stop, and then you put the torque limit down to 0, and then you let the other motor, you just jog the other motor and let it turn the other one while you trace those values that are in that document. So instead of turning it by hand, you would just turn the other one, you would turn it with the other motor, and you would look at that trace. That way that you're not going to damage anything in between the two. I don't know what is connected to your process on it, but if it was just rollers or something that you're able to turn them freely, that's how I would do that. I wouldn't want, you're right, I wouldn't want to do a pole ID function on something that has a connected load to it, because it's going to go back and forth. And like a chain, you wouldn't want that. You would at least want to take the chain off and decouple the load. So what I'm trying to, what we're about to do load sharing. I have, so kind of OG, you're talking about 300 kW, that's decent size, but not too bad. So for that, honestly, a rotary shear and a rotary knife is pretty much the same thing in terms of kind of the motion control. And I'm trying to think in my winder, how to build a winder. You don't want any jerk during position. Pull position. Right. Yeah. Akhlad, I would not do the pole ID. I would not run the pole ID function. I would do the yeah. So I would not do the pole ID function. I would use the other motor to rotate the drive, or rotate the other motor. So if you have two 400 kW motors, that one 400 kW motor should be able to turn. If they're still coupled together, if there's some way that you could decouple them from the actual machine, use the other motor to rotate it. That's the only way that you're going to be able to do that. And honestly, you probably, yeah. So OG, I mean, that's a flying knife. So our winder is, I mean, it uses that technology, and really all you have to do is use a absolute gear. And I want to say that's a motion. If OG, have you watched the Motion 101 live stream that we did a couple weeks ago? I guess maybe last week. Yeah, so in the Motion 101 class, what I did was I talked about the absolute gearing. And if you use an absolute gear, um, if you use an absolute gear function, when you set that function up, um, it will go through and it will sit and wait, and so you'll have to figure out your position on your leading axis. And so your leading axis, you'll figure out a position, and you have to make sure that you have enough power to accelerate your shear to the speeds. And one of the things that I did, I'm trying to think if I have a picture. And Akhlad, I will go through those steps here in a second. Trying to think if I have a picture here of like of the winder, because it has because it shows. So basically on it, your shear is going to be rotating around, and as your point comes around, you need or a bit. Yeah. So one thing that I will say on, you shouldn't be. Oh, so the calculation for the length, I'm not sure how. Yeah, that's if you don't have a good way to like calculate where to make that point. Um, and yeah, so what I'll do for you Akhlad, I will kind of detail out on a document and put it and send it to you, or at least put it in the thing for it, because the document that we'll be putting in the drive, it details out step by step what to do. You're just going to have to turn it by the other motor. So I'll do that for you. We'll kind of move on to this other topic. For OG, that I don't know how your system's set up in order to calculate your position. In our winder, the way our rotary knife works is we have our system is in degrees, and so everything's in degrees, and so we are calculating out how long our roll is going to be. And so all I'm doing for that roll is saying, I need you to move an absolute move of, a relative move of whatever the roll length is in degrees. And what I do at that point is go back. What's up, Angel? What's up? What we do at that, we fire that relative move, and the calculation is how far away is my cut? Where am I wanting to cut? And I'm just doing a total length minus my cut length, and then that's going to be where my cut point is. And because I have linearized my system all to the same degrees, so I've normalized, should be a better word. Since I've normalized my system all to the same degrees, then all I say is, all right, my parameters on my gear in function are, I have to give it enough distance in order to speed up, and that's based on the size of your motor. But then I calculate out where my blade, my shear tip is. So what I calculate out where my blade tip is at 0, and then I rotate it around to the actual contact point of the material, and then I measure that. That is going to be my my slave sync position, and the master sync position is just going to be that length minus cut length. So ours are much smaller than that, I will say, but it's the same calculation. It's the same principle. I mean, I think we're 15 kW on our motors, so much smaller, but the calculation would be the same, and it's based on the physics of of how big your shear is, how much power you're needing, what speed. So you're talking about kind of accelerating away and getting away from the shear point. If yes, I'd use the TCPU. Just right, because you need the absolute positioning on it. And so use a TCPU. I use a 1515T. I mean, and we have like 10 axes or something on it. I mean, we had 2 control units and run it all on one TCPU, and the so yeah, so TCPU. I will answer your question here in a second, Angel. The Pros Motion D, but it's useless for me if I need an example. Oh, so if you're programmed in Motion D, it's basically the same thing. So, are you writing your motion program in ST or MCC, motion control charts? Because that's kind of the big question here. Did I not? Basic system. Big system. Yeah, so okay. Well, MCC, you can, with motion control charts, you can still do the same thing. So there is an absolute gear in function. It actually has the same parameters as the functions that are using for the TCPU. And so you still have that master sync position, you have the slave sync position, you have the gear ratio numerator, ratio denominator, you have the mode profile. All of those are going to be parameters in the motion control chart function. So when you activate the in your flow, when you go through and activate the gear in absolute, if I remember correctly, you can like double click on the block and it goes through all the parameters and sets all of them. And so that's where you can go through and generate those different values. ST is, yeah, I mean that your parameters and your values, wherever they're coming from, if that's coming from like an HMI, then that's going to be in your Motion D interface. And of course, like Ali Reza's off fixing a plant and fixing his plant, and this is the first time I'm actually talking about Motion D on it. So when you're watching this later, Ali Reza, you see I'm finally talking about Motion. But so wherever your parameters are coming in from your HMI into whatever dB or whatever, that is going to be what you're going to be using in your little motion control chart for the function for gear in absolute. So that gear in absolute, you can look at my video, like the Motion 101, explaining the MC gear in absolute functions, the parameters. Those are pretty much the exact same parameters. That you might not have different, like the different load profiles might, or accelerate sync profiles. The sync profiles might be a little bit different, like the actual numbers, but you're going to have one that you have a sync direction, sync, all of that is going to be exactly the same. You're just going to have to figure out how you're making your move, and figure out that master sync point where you want that blade to hit, and then everything else is going to be the same. You set your blade at 0, set it up to where your blade's at 0 on your following axis, and then just jog that blade down and figure out where it's making contact, and then that's going to be, that number is going to be your slave sync position. And as for the separating out, just set a ratio that is higher than 1, and what it'll do is it'll shoot forward. And so instead of being in sync like that, and so it'll actually separate out. The problem is you have to ungear that function after it's geared in, because if you keep moving that master axis, that and it's still geared in, your shear will still, it'll come back around and double shear. So you need to have a function that goes in and makes sure that it catches it from going back around. And in our case, I have really 3 levels. So I have one built into the sequencer, and so the axis itself is like saying, okay, at this point I'm stopping, I'm hitting a halt. And then there's a second level that's saying I'm going to fire a homing move. And so it halts and then homes. So there's 2 separate moves that are trying to stop it. And then I have a monitoring function that's kind of like a supervisory over the top that monitors everything, that if it sees it goes past, it does an e-stop on it. So like it hits an e-stop on the drive itself, and then the TCPU will fault out and everything because it's not expecting it to be out. But especially in your case, you need to make sure that once it's geared in, you're basically immediately gearing it, like firing something else. You're either firing a halt, which will stop that gear in, but you don't want it to stay on. The only other thing on that gear in function is to make sure that while you are actually waiting, that if for some reason your process stops, that you cancel the waiting gear in move. Because that gear in move, if you start jogging the master axis, it's still going to be geared in. It's still going to be waiting on that gear in. So there's usually an output on that MC gear in absolute block that is it's something to the effect, in MCC, I don't remember what the output is, but it's going to be, there's a busy and then an in sync. There's 2 different things. If you are busy and you are not in sync, that means it's sitting there waiting, and you cannot allow the master axis to jog, because if you jog it, if it's in that situation, you might end up taking someone's hand off or taking someone's head off. And so just very much be very careful about once you've activated that gear in function, to make sure that it is not active if you are moving the master axis, because it'll move 9 times out of 10, whatever, you reset it up, but then that one time they keep jogging it, and all of a sudden your shear goes shoom, and just like randomly. And I'm not too proud to admit that I know this from experience on our winder, that in the TCPU, that the halt does not cancel the MC gear in waiting. So like while it's waiting, an MC halt does not cancel it. You have to use an MC stop. And so check that on your MCC charts, like just to make sure that you are actually canceling that move. And if you're using a halt, like make sure it actually cancels it, because it's very important that that's out. So wait, so you're telling me this is a dual motor shear? Is that what you're telling me? You've got a fun one. I want to come over there and help you on that one. That sounds fun. So What you could do on that is, I mean, you're going to have to put some layers of protection, but you can do a saturated speed controller. So the same thing that we're about to talk about in this torque sharing, then you're going to kind of go into the same thing. Man, oh, here it is. So it's this one. Because I've kind of talked quite a bit about these functions. I think you're kind of talking. I don't know. What was it? Was it you that were asking about the? Were you asking about the master follower failover and automatic? Was that you that was asking that? I kind of lose track of who's asking who, or who is asking what questions. Oh, well, yeah, we kind of talk about how to make that changeover automatic. Okay, so because that was what I was wanting to talk about today, just about the load sharing portion of it, and it'd be good to talk about it because I think it's I think it's applicable in both situations. If you don't really make sure that you really understand the saturated speed controller setting, because in this situation it's going to be a little bit more difficult, because you're going to be having a motion control axis. You're not going to be able to do the master follower or automatic changeover in your shear application. It would be very difficult, and honestly, yeah, I know it's a continuous process, so you really need to be able to have redundancy in that cut. But yeah, so but on this one, let's talk about the automatic changeover, because what you're always going to be doing in these applications is you're going to be sending the master actual torque over to the following axes. You're going to be sending the master's actual torque over as the follower's upper torque limit. So what I wanted to do, and gosh, this load sharing application is rough, but we got too much stuff in this. I'm gonna have to clean this up before I put it into the what's it called, the member drive. But let's see. So what I was gonna do, let's go through and make a block, because I want to make a function block called we're going to make a function block called load share drive control, and let's just build on this. I mean, we've only been going for almost 3 hours now, so let's toss on another couple hours. This is what I get for being gone for a week. I know. I try to make it up to you. Which, by the way, if you're just joining in, welcome to the stream. We're probably going to be going for a little bit more, so go ahead, hit that like, just get the stream out here. This is your first time here, and you like the way we're doing these things, you might want to check out other videos on here too, because we've got a lot of content. Try to do one of these every week, and we've got a Discord channel where we're talking back and forth. But yeah, we're just a group of engineers trying to get better, trying to improve our lives and the lives of those around us. So if you like that sort of stuff, check out the rest of the content, and hopefully I'm gonna earn a clicking that subscribe button. But yeah, so we are going to want in this, honestly, let's just do it this way. Let's bring in a DB called drive data. And what a DB any is a pointer to a function block. Or actually, I don't know if we're going to be able to do this because we'd be able to do offsets. We probably want to bring in different stuff. No, I want to do this a little different. We're not going to do this. We're not going to do a DB any. We're going to make a data type. Okay. We love our data types, right? And we are going to do load share drive data. Okay. Seems pretty good. And the reason I just wanted to go ahead and do this, compile that. Gosh, that's... Oh. Now I can compile it. So the reason I wanted to just make that is so drive data, I want to make this a type ls drive data. Now what that means, so is that gonna work? No, yeah. Except we want this as, yeah, this is good. Hey, I totally agree with you on that. Alan Bradley can't do tough applications. Like, write it down. I didn't say it. OG said it. Like, check it right there. Yeah. I mean, if they're using Alan Bradley drives, probably the regenerative load on them will pop them like everything. Which, anyway, I'm not here to talk bad about Alan Bradley. I'm here to tell y'all how to use Siemens. but yeah, there are definitely some applications that Alan Bradley does better than Siemens, and it's easier to use them. There are also a lot of applications that I've found that it's just a nightmare to try and do. So I believe in. So let's go through, and we're making this. And again, we're going to kind of do a couple of different topics and kind of cover a lot of different stuff. And again, I don't have my professor outfit on today, so we're just kind of going through and talking and spending time working on these different things. So if you're coming in and you're watching this and you're at a different level in your automation journey, like, try to find something that you can cling on to. We're going to be using a lot of different things, data types, function blocks, so maybe there's some stuff to learn. If you have questions, be sure to drop them in the chat. But I am going to, I almost forgot about Angel's question. So I do think it is possible, Angel, if you're still here, I do think it is possible to get your data out. I'm probably not gonna have time to go through and do the stream, but I probably on the next stream I'm gonna build you kind of a heart block, because I'm gonna show you. Well, I can show you real quick this data type for the heart. So like, let's do something for like that heart data if I can remember it from. Got a couple of different things that are going, and again, like I said, this is what I get for being gone. So what I was meaning by you need a, the next stream will probably be next Monday. I might try to stream a little bit, but if I remember correctly about the issue that you had with your data was there was a Boolean that was like a type. So it was like, parameter type like that, and that wasn't a Boolean, so that was a word, and so that was a single word, and then you had your parameter value, which was a real. Okay, so this was kind of the setup, if I remember correctly. And maybe I can, let me just flip over here real quick and look at your text. I remember. Sorry, I'm just looking in the chat from what we were talking about this, because that was in a thread. Real, then a word. So I got these backwards. So let's flip these. So like that. And then, so we got that. So now we compile that. And so what we can do is add a new block. So make a data block called like my heart data, global DB, when we can access anywhere. And so you have those 4 heart parameters. And so you'd have para 1 like this, and you're going to make that this type of heart data. And then we're just going to say para 1, 2, 3, 4 like that. And now you have inside of here this structure. And so that's going to organize your structure the proper way, because you have a real value and then kind of a command value, because there was that extra word. Yeah, because you have channel, you have a value and a quality code is what it was. Sorry. So I got the name of this is wrong. So this heart data, this is like quality. Compile that, and that should propagate over to here. We hit update interface, blah. So this is what you actually need in your data block, instead of just kind of like the raw parameters. So I actually have on order one of these heart modules. I don't know when it'll actually get there. So, but when you kind of like are pointing your data, because like what I'm looking at in your thing here, so your read record, everything needs to be the same. So you have your ID, your index is gonna go to right here. And then if we go and look at this, if we go properties, optimize block data off, optimize access off, it gives you, when you compile this block, it actually gives you your offsets in here. So there's all your offsets. And so your M length on this will be 22. See? Simple. Yeah, so you'll be pointing to the same place, and so your ID, get it to the same place, and then your offset will be 22. And as it populates in all of that, because of the order that heart data is coming in, what was happening with your data was this word was getting in the middle of your real values. And so you were going like reals. Yeah. And so that should work from what I could tell. And so heart data is cool stuff. If you don't know what it is, it probably about to have a stream on it here in a little bit. Hopefully I'll have some hardware to work with on it. But it's using read records, data records, and to get extra data out of like your regular sensors. Like a pressure sensor has a bunch of other stuff in it, and heart is a way to get that data out. And so we'll probably have another stream on it, but it's pretty cool stuff. But let's get back to our load share drive control. So what we're wanting to do now that we're going to be building this LS drive data, and what we're going to have is a block called my drive data. Okay. And we're going to say we have a 4-axis load sharing system. So we're going to have drive 1, and it is going to be of a type load share drive data. And obviously we haven't built this all the way out. And if we have 4 of these drives, we're going to do this right here. And it's not going to do anything. We're going to do it again, and it's going to do something. And so we have drive 1, 2, 3, 4. Nothing really in there right now. But as we update this data type, we will be able to do this. So what we'll do, the structure of this like drive data type. All right. So let's just give ourselves, say, 16 bools. So we want to add 15 elements because we want to just give ourselves some space. And then we're going to start with a couple of set points and things. So what we'll do is drive speed set point. We'll just call this a real. That may not be the best thing, but we want to do whatever. We want that in percent, so this will be in percent. Drive speed set point. Upper torque limit. Lower torque limit. Is that all we need? Okay, maybe. So we'll do safety. Enable. Run. 3 different things. So safety obviously is an e-stop circuit, so we're going to tie that in our little function. We're going to tie that to the off 2 or off 3 input, probably off 3. The enable is going to be used to designate whether or not you are actually using that drive, and the run is going to be the actual run command, so the off 1 command. So the next thing we're going to do is we're going to say is master. And if that is true, it will be the master. It's crazy, right? But so what we're going to do is we need these couple of things, and we may want more, but this is just the general structure. I'm just kind of going through the basics of kind of generating this, the thought behind going through and swapping everything. Because you might want to have other things. So we're going to save this, compile this, and then go back to my drive data, and it's going to be all complainy and stuff. And now we have all of our stuff in there. So what we're going to do is kind of in our load shared drive control, we'll update this interface as well, because now we have all this stuff. And so in this, we're going to say we're going to have our safety loop, and so here's one of the things. I have this ag drive tel 352 out. All right, so for my output, I'm going to have my drive out, and that is going to be an ag 352 tel out. So the reason I'm using this, and you can go back and watch the load sharing video. And by the way, I guess I have my microphone then. I got some new headphones, and I didn't realize how horrible the audio was with that other microphone. This is pretty good, but it still gets, so I'm sorry for my old videos. I learned. I appreciate those that like my headphones just weren't good enough to hear how bad it was. And like my TV, it's totally fine, but to put them on these things, I'm like almost want to like not use them. So input, we're also going to bring in this drive input, so the Telegram. And again, these are the tags that we would have created and linked to the IO addresses for our telegrams. And we're using the Telegram 352. And this is a special data type that I have made because, let's open it up. 352 Telegram out, because there's some user PIDs or user PZDs, and I have tied them to the upper and lower torque limits. Look at that, isn't that cool? But it's using everything that is exactly the same as 352, and Telegram 352 has these 4 words that you get out, and then on the input side, I think there's like, yeah, it automatically has the actual torque, actual current. So we'll do that. So what we're going to do is inside of our, and I'm not going to go through this. Honestly, we've been going for over 3 hours. And for all of you that like watch these either live or on demand, I appreciate y'all staying with me so much. I can be long-winded. I like talking about this stuff. And yeah, so I'm glad that y'all are here. So with the in out, yep, so that's good. So we'll save that. And the reason why we want to use an in out here is because we are going to be modifying these values, or we want to be able to modify them freely. If you only have an input, you can't change input data. So like I can't modify the structure, anything in here, like in this logic. But if I were to use this as an in out, I would actually be able to modify it, because in outs are what would essentially be passed by reference instead of like actually passing by whatever. It's like making a copy. It's just referencing the whatever you pass to it. And so when I go through here in a second and pull up this block in my OB1, it is going to actually just be, it's not going to make a copy of that data. And so it's just going to be in the reference to it. So it's pretty cool. So safety, obviously, we're going to be doing a thing here for this, because we want, if our safety is on, actually, we need to do always enabled. Because there's some of these things that you always need to have on. And so what we're going to do is we're going to make a constant is called all, or I like saying no op and then making it false, because that's the default and I don't have to change anything and I'm lazy. And then do not no op, which means it will always be on. And we're going to have a couple of these drive outputs. So we need in our control word, we're going to need bit control by PLC. We're going to use, we just want that on because we're going to do quick stop. We want an enable operation. Da, 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 da. Do, do, do. But so enable ramp function generator. And don't ask me why all this stuff is in here. Unfreeze ramp function generator. There's reasons for all of this. enable set point. Look at that. All that's cool, isn't it? And so you can do save now. So those are your always enables, and that should get you going. We've got control by PLC, no co-stop, enable operation. Yep, that should be good. So those are always on. Now we want our safety. And we're gonna bring in yeah. And yeah, so just a little bit of information about this, because the way I'm organizing all this stuff, I'm gonna end up having static memory. I'm using everything, and I'm kind of like, this is kind of a use everything type of situation, and that's kind of why I wanted to do this. Constants, temp, I may have temps here later after we build this sort of stuff, but so we're gonna take and so like speed set point, and then we're just gonna take for this, we're just going to do a move. Are we? Yeah, we are. We're gonna take just a speed set point from here. Drive speed set point, because we're about to convert this to, so this is in percent, remember? The drive speed set point in percent, says it right there. Somebody smart said that. OG, my company is located in Sweet Home, Alabama. It's a bunch of rednecks down in Alabama. It's also in the same county region as the only Mercedes manufacturing plant in the US. So if you drive a Mercedes SUV, by the way, you can thank a redneck. Yeah, so it's out of the Tuscaloosa, Alabama area. So all those people in the US are like, oh my gosh, this Alabama guy. So temp, I don't think I could do a, because we're about to convert this into a we're about to convert this into temp. So what do we need to do? We need to divide. Actually, instead of doing a move, let's just do this divide. Or is it multiply? Percent. Oh yeah, that'd be awesome. Yeah, that would absolutely be awesome. Yeah, so so you're, I mean, yeah, we'll definitely get the contact information. I mean, you're in contact with me either in the Discord, you can hit me up, DM, or WhatsApp if you're already doing my WhatsApp. But yeah, so let's go through and, because we're going to multiply that. Let's change this around. Multiply that by, what is it? 16, 3, 8, 4, and then move the decimal 1, 2, like that. That's how that math works. I think so. Looks good. It'd be really awesome if I could just like shove this into a dent. Can I? I always forget sometimes what Portal can, it's implicit conversions. Sometimes it just like randomly I don't think it can do this because there's two different ways to get a dent. Maybe I'm wrong, because you can either round up, you can either round down, or like you can truncate or round down, or round. So I'm guessing this is just rounding, but whatever. If you don't know what I'm talking about, so a real has decimal points, and what we're doing is we're converting the speed set point. Everything that goes to the drive is a percentage base scaled 0 to 100 is 16384, which is 14 bits. And I explained that a couple of different times on all sorts of different stuff, but it is something that you just got to do. You're scaling to 16384 all the time. And so if you go over 100%, you get that extra bit, so you can go up to 200%. And so that's just what I'm doing. I'm making a number that is scaled to 16384 based off of this reel that is, yeah. So in the telegram itself, it is technically yeah. So it's a integer, and so you send that 16384 over as an integer, and so there's no decimals. So a real is 4 bytes, goes to a double int, and then you can do a converter into whatever. I wonder if it can just go straight into it though. Drive speed set point. Nope. Wrong place. Drive out is a word. Can it do it? No, because it doesn't know what it is. So let's just go back and do it this way. I don't really like the fact that that's a word, but we'll do this because I'm pretty sure we can just do a convert. Where's my convert? It's down here. I think I just like do it. Temp dent into the speed set point. I don't like this. Oh, I see. Just call it an int and get over it. Yeah, that's how that works. I'm sure that you could probably do that explicit conversion there, but so see, we've used like every type, and my eye is really itching right now. Sorry. So we've got that. That's a speed set point. Now let's do this real quick because I want to show you for torque. Limits, something that's really important when you're working with torque limits. You never, ever, 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 ever want to get back together again. Wait, that's a different song. Sorry. You never, ever want to put a negative torque limit into the upper torque limit or a positive torque limit into the lower torque limit, because things go crazy really quick. So what we're going to do is we're going to do this basic math, right? We're going to bring that down because all of this still needs to be, this is upper torque limit, and we're going to take out of our in and out down here, yeah, upper torque limit, like that. Same math, but in between here, we want to do an absolute value function. Where do we want to put it? We're going to put it here. Yeah, absolute. Can we do this? This would be cool. So yeah, we'll just do another one. I always make these like, so back in the day, back in my day, in S7, you always had to, or in Classic, you always had to have like these little temps because there wasn't as many explicit conversions, and so you always had to like do this sort of thing with the temps, and I just get used to it. So for the upper torque limit, that's good. It needs to be positive all the time. So no matter what, it's gonna get that. So we could also, because your actual value is gonna come over here in a minute, and basically, if we'll talk about it in a second. There's something else that's going on too, but and then we have to multiply this by -1. Does anybody know of a function that is like the inverse absolute value, like a not absolute, like always negative? Because that would be cool, because that's what I'm about to do, because I'm just going to multiply. It's a real. Obviously it's a real. Well, that would be dumb if it was a real. No! It's not a real. I lied. It's an int. -1. There. Now you're happy, right? Temp. Int. Temp. Int. Boom. Alright. So now we've got our torque limits to where they won't go crazy. So that's really all we really got to do. Let's see. Yep. And so we'll do. Oh, I didn't do start. So Control R and let's do it this way. Yeah. Make it like that. And see, if you're not used to making function blocks, you always want everything inside your function blocks to have the hashtags. If it doesn't have a hashtag, it's not a good block. Yeah, that's a lie. Obviously, this doesn't have a hashtag, so I'm a liar. But seriously, if you don't have a hashtag in there, that either means you are referencing a global, like a M memory, or you are referencing a global hashtag, or a global data block. Now, there's absolutely times where you would want to reference a global data block, but the whole point of writing this function block is I'm about to bring in 4 instances of this function block and then just tie them to the individual tags in my data block. I don't want to have to go through and re-type out all the tags inside the function block, and this is how you accomplish that. So I've got all of this, and so now let's just collapse all of that, and that's really all that is. What's this? On? Yeah. Off 1. We'll call it that. So we're going to save, compile. Now we're going to go into main. All right, and we're going to see. This looks fun. This looks like I did it like, and I'm sure that I was on. Yeah, we're deleting all this stuff. You don't want this stuff. I know what I did. So we're cleaning up and making a little bit better this load sharing example from however long ago this was. So we'll call it drive 1. All right. Now that we've made this, we just say pop this and we say drive 1 control. It's a single instance. Now what I can do is, so I have my drive data here, and I want this drive data needs something, right? So drive 1, bloop, and it's happy because this drive type, so this LS drive data, if we sit and hover over this, it's looking for click, and hover, it's looking for an LS drive data. And so now I just do the same for drive 2. And what's crazy is that actually has connected up everything. So let's see, do we have our tags master and master? Okay, so yeah. So we only have 2 drives in this one, which is fine, but we already have our tags. So I don't like what they're named because they're a little bit confusing for what we're doing, because we're gonna make it to where you can swap everything around. So all right, so we're gonna have drive 2, and we're gonna bring in another one of these, like that. Drive 2, driver 2. Those allergies are going crazy. It's pollen season in the U.S., southern U.S. Drive 2 control. Got that. Now we just grab drive data, and then we drive number 2 there. And so I've made this like global data block that I can access, because I'm about to start modifying some of that stuff, because you want your drives to act exactly the same. So you want everything exactly the same with them, and then you want to have a wrapper outside of that logic that's saying, all right, I'm modifying this data, okay? And I'm going to do that here. I mean, shoot, I might even just have a function call or whatever for it. That's what we'll do. I'll write a function call. We had a couple of people that were a little having questions about the best way to organize memory. That's maybe why I'm kind of doing things the way I'm doing, is to show you how to make a good function block, how to use different memory areas, and how to use function calls and data blocks, and how everything's working. So all right, so what we've got this tag table here. Blah blah blah. What were they called? All right, so at first we're gonna call it master drive in none. By the way, I need the whole thing. I'm bringing in the whole telegram, and if you so like this input is of a data type. If this drive input, I don't know why it's not allowing it to pull up. So it is that AG352 drive tail in data type. And so it's basically wanting a pointer to a certain thing. And so it'll let you mess these up. But one way is if you leave a dot there and then just click out, it doesn't like it. But if you delete the dot, so if you delete the dot, enter, you have to click none, and it will just point to the start, and then that's the type. And so you kind of think about it like in the default tag table, it is going and saying this is none right here, and that's the data type. If you go down one level down here, this is a ag ZSW1, right? So the only reason it was allowing me an option to kind of dig down into this, I'll show you this. So like, we'll go back to this master drive out, and it's going to the control word, and there is nothing in the control word of the type AG352 tell out. So it's like it doesn't give you any options. So that's why it's kind of broken here. So we could just scroll all the way back, hit that, hit none, because that is the type, and it's perfectly fine. Long-winded explanation, but yeah, whatever. My blood has not been compiled. Oh, yeah, okay, yeah. So now let's get these other tags. So I think this was follower drive in, none. Follower drive in, nope. Drive out, none. There we go. So now we've actually connected up those drives. Now that drive data is connected in to where these data blocks, if we modify these data blocks, this block loads that in and handles it. And you're like, why didn't we just handle all the stuff inside the block? Well, because we want that wrapper. Because if drive 1 is the master, it's going to act one way. If drive 2 is the master, it's going to act that way, and vice versa. And so, like, if one's a follower, then it's going to act differently than the master. And what we're going to do is we're going to set up a way to where if one drive is still running, it's not going to fault out and say, oh, hey, like, we're going to have an automatic, I'm going to go through a scheme with how to do that switch over. So what we're going to do now is we're going to make a new block, and we're going to do a function call this time, because this is just going to manage, it's going to be looking at data from different places, and it's going to say, okay, I've got this data, I've got these tags, I've got this stuff, now I want to modify stuff. I don't need to store anything, everything's elsewhere. And so that is a function call. And so we're going to call this, I don't know, drive, or system control. That sounds cool, especially for an FC1. And so what the first thing we're going to do is we're going to say, like, we need to set all of this data in this thing. So we need to set is master. So you can select that. I mean, you could select it from the screen. So it's like there has to be some sort of priority, because you can't have multiple selections. But we're going to assume that you understand that and you're going to set that up. And so what we've got here is we are going to look at if drive 1 is the master, then we want to move we haven't polished those inputs. I just thought of something. We haven't converted our inputs to percent. So I almost made a mistake, and I'll show you what I mean. We'll do that here in a second, because we're wanting to move the if the drive 1 is a master, then we want to take the value. So we just divide that by 6. Okay, so what we'll do, we're going to take this. Yep. So we take this value. We're going to look at the tag. So this is, we'll call it the master drive in actual torque. And remember, that's that word, or that is in, that's a percent, right? So we need to convert that. So actually, let's see if we can just divide that and it be okay. I want this to be a real. It won't let me. So this is, it can't, so with this. Now, we can still have temp memory in here. Temp, real. Again, the difference between a function call and a function block is a function call saves nothing. It has no way to actually save anything. You are dealing with inputs that don't get saved, outputs that get put out, and then in and out, which is technically being, yeah, you're saving there, but there's no static memory. Whereas in a function block, if you use static memory, that's there. That's in the instance DB. So, but temporary memory, I need to convert. Uh, a convert. What? Why are you not letting me do a... This needs to know what this is. Int to... Oh, that's why. I didn't know that was an int. So that should be totally fine. And so now we're going to divide this by 16,384.0. That's going to get... Nope, that's not right. We're going to divide this by 0.2. There. So, doing this. And that is going to be our drive 2. So my drive data. Drive 2. That is going to be... Actual torque is going to be upper torque limit. Right? But if we look at that, if that's master, that actual torque needs to go to the upper torque limit. That's if it's positive, right? So let's think about that. So let's look at comparator operations. So if this is, I guess we could do greater than or equal. Like this, if Yep. So doing this is like real world, kind of like what we're doing. We got to make sure this. So that is that. Actually, so we can do that to a real. And do that division. Our code can just I'm just obsessing over the best way to do this, because we can do this comparison out here, or we can do this comparison over here and either move it to the upper or lower torque limit, right? So I think I want to do that. So do this every time and then move this over here, and so temp real. Oh, because this needs to be a real now. Real. Temp's greater than 0. Move. So now that's getting done. So you have to load. That's drive 1 as master. So that's the limits for those. We can kind of do now. So we just have our whatever speed set point. And so like our overall system speed set point is going to be down here. So we're going to do this. So if that is master, we're also going to move the speed set point. to everything, right? So we're going to do move so oh, we don't have a tag named that, so we just do this. Rewire, that needs to be real, because we're looking that to go to drive 1. That is its drive speed set point. It converts it, and that's good. So if you're master, if this is master, then you want it to be doing that, right? So you want it to have its own, the actual system speed set point is set. The actual, so the actual torque is getting sit out to there. And so, and if it is the master, we also want its upper and lower torque limits to be set to. Did I do this right? Yeah, because that needs to be in real. Yeah, and so we can just do this. So move. So we're going to say 100.0 to upper torque limit for drive 1, and then negative 100.0 to lower torque limit for drive 1. And the reason why this comes into play will get a little bit more obvious here in a second, but we have to set the master, we have to set it. So if drive 1 is a master, then you need to be sending the actual torque of drive 1 as the upper or lower limits of the following axes. And so this would be the same for everything. And there's, like, the thing about it is there's another way to do this. So to where you could set this as, to put this logic, I kind of like the idea of putting this logic into the function block, and you just say master torque, right? And then all you're doing is saying what is the master torque value, and then that is based on what we're about to do. But for this example, since we only have 2 drives, it's kind of like easy. But if I were doing this for this, I would have an input up here that says master torque value. Let's just do this. Let's just do this then. This is a better way. We're going to do it the right way. So this is a real value, master torque. We'll save this. And then we're going to take this logic that we just wrote here. Where is, because we did upper torque limit, lower torque limit here. Yeah, because you would want to be able to manually put that in there. You'd want to be able to modify that out in different places, like the master torque. Yeah, so I'm just kind of thinking about some actual situations that we ran into, because the way that the programs that that were written that I'd worked with in this were written before I got involved with them, and they use function calls kind of similar to what I was doing here. And for each one, they would go through and set up and kind of modify these global blocks. But why do that if you could make a block and you could have multiple? So 4, 5, 6, 10, whatever, that could all be running off of the same thing. Like if you had like a table, like an ingot table, roller, like a roller mill or something. My goodness, we're coming up on 4 hours. So let's just go through. Again, like you would do the same thing because you're wanting to send the master. So blah, 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 blah. See, yeah, I'm gonna do this. I'm just gonna make it the right. I'm just gonna do it right. So temporal. So let's do this, and we're gonna make a master torque. And we're gonna just name this. This needs to be in a global data block, but I'm just gonna do it this way, just because, yeah. And so now we're just gonna take and we're gonna delete this, right? And so this is percentage based. So, and then now we've brought this into our load share, right? So speed, torque limits. Update up. We're just gonna say that converted that. This is me actually thinking through the best way to do this. So you could put that logic in there. So the master torque is always going to be, yeah, your master torque limit. Oh yeah, that's your master torque limit is always going to be. Oh wait, let's look at that. So if that's the master, you're going to set its upper torque limits and lower torque limits, right? Okay. And that master torque is there. Oh, if that, oh, I can put this in, I can put this here into the block. I'll show you. Because in the block, it's gonna have, this is, since this is drive 1 and this is drive 1 and we're passing it drive 1 data, we can put this into the block. So we're gonna X that. Go here. Go down here, and this, and then just say, because this input is for this block, well, not this one, this in out. We're just going to put this right here because that is for this, and then we're going to change this to because remember, gotta have the hashtags. Gotta have the hashtags. So, all right, so that looks a little better. So, drive it up torque limit. So if it's the master, we're gonna give it actually. So, huh. We can just do this. Hold on. So if it's not, I like this. I like this better. So put this down here. Blah blah blah. Dot. Come on. Da, 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 da. So if it's not the master, it puts master torque in here. Yeah, I like that. I like that because that takes away that takes a lot, because that way you're looking at just the master torque, and doesn't matter where the master torque's coming from. If it is the master, then it gets 100% torque, and that's built into the way that we're passing this data. So I kind of like this. This is again an improvement on or kind of thinking through the way that a system that I have worked with before is done, and kind of just taking like, oh, if I could do this a different way, how would I do it? And so now, if drive 1 is the master, then it needs to put the convert and put that as the master torque. And then the system speed set point needs to be put to the drive 1 speed set point. Okay. And those, so if it's not the master, gosh, we could just almost do all of this in the thing, because so yeah, we could, gosh, yeah. So your system speed set point needs to be passed into this block as well. Cool. See, we're learning as we go through here, and the reason, so like the automatic changeover kind of started making me think about like what is actually necessary in these data blocks. What do we really need to pass back and forth? And so it kind of got me thinking about this. So I'm glad that you asked that question. It's really good. So we got our torque limits. So let's look at our speed set point. Let's add into this another input, and let's call it, let's insert a row. System speed set point, and it's real. Okay. So, and let's kind of take about, if it is the master, the drive's not the master, like this, we want to take the system speed set point, put that there. So if it is not the master, and if you wanted to, so we could, here, I'll do this. Static. Saturation percent. We're going to do a real value. Okay, so, and what the saturation parameter is it is trying to force the following axes to jam up into the current limit, and the only way it can do that is for it to try and run faster than the master axis. So that's what the saturation parameter is. And I mean, you got to multiply the speed set point times the saturation parameter. So if it's not, then you just send it. If it is the master, then you just do this math without that. You just do that. You just convert the system speed set point. And so you're just passing that in. So we don't even need, in our data block, we don't even need half the stuff. We really are just needing the, because do we even use that stuff? Master torque, nope. That's going straight to the telegram. What is this other block? What are we doing with this other block? Oh my gosh. Okay. So, all right, I should have thought about this a little bit more, because, I mean, we don't even really need this global data block. Because I guess we do. That's good. We definitely need it, because we just don't need these values in there, because those are based off of different things. So anyway, so I kind of like this. We might, because let's open this up and just look and see if there actually is any. We definitely got those drive outs, drive outs, drive outs, drive outs, drive outs converted. But yeah, so this actually gets us now. Let's compile this. And then come here and surprise. Oh, that was in OB1, wasn't it? I'm like, what? I changed the interface. Yeah, I changed the interface. I'm gonna have to add in some new stuff. I know. So when you change the interface on a block that's already called, it's gonna do what it just did, and you have to go in and add in the new interfaces. So this is system speed set point, and this is master torque value. And again, we're gonna go through and set these with our little control master torque value. So now that's set up to where it's doing all the torque sharing stuff and even doing the speed saturation, so which is cool. So now let's go back here, and so let's look at this. So master one, so it's already looking at if it's the master, and so I can just delete this. So the only thing it needs to do in our scheme is sit and say, all right, I need to throw my actual torque into it, right? So what we can do now is just copy this and then just say drive 2 is master, like this, and then this is backwards, isn't it? Oh no, follower drive in actual torque. So toss these in. I forgot these are named. So we've got our two calls, and we are looking at the two different things. And so master, follower, master torque value, master torque value. Yeah. So the only time that this is going to be selected as a master is going to be this. So it'll execute this. So now we need to say if I want to do something real quick, because you do need to do this in like a real system up at the top. So you need to have some sort of hierarchy. So it's like if like this, like that, you need to do like a set. Because what did I just do? So you want to do something like this, and have some sort of hierarchy to where it's like because you have to figure out some way to like set like a default. And in this case, it's we only have two. If that one's the master, it's going to reset. So if drive 1's a master, it's going to reset the drive 2. So the only way that you'd be able to do it to get drive 2 the master is being that it is this. But I want to do drive 2. If drive 2 is a master, we want to do a reset. And I think that this would be an issue on something on our quick failover thing, because what we're about to do is we're about to just swap masters, and so essentially up here you would want to do your swap you'd want to do your swap kind of logic down at the bottom, and then you would go up, and the next time it comes in, you're like, hey, if this is faulted, turn drive 2 as the master, and that means it gets everything swapped. And so if it comes in, see, that would be a problem. So yeah, if so, all right, that's good. I mean, that's good to know. So, and drive. So this is going to be, and so we need to look at the fault. So the input, so status word, fault present, and let's do this. So this will actually be kind of the same logic. So, I did this wrong. So if it's a master and there's not a fault present, then, and we have drive 1 enabled. That seem right? No, I actually won't. And you want to reset that. I think that's kind of close. And if it's running, for some reason, I just have a feeling that we need the master drive in, status word, operation enabled, that. And then we do the same sort of stuff. So if drive 1 is selected as master and it's running, it will reset that. So you don't have to do that on drive 2, just because it's second in the logic. Because if drive 2 was the master and it automatically swapped over because of a fault, this would trigger before it would reset it, and then it would get down here and it would not be there. But what we'll do, just so that it all right, so here we go. So what that does is later on down in the bottom, this is just checking to make sure that there's only one master, and that is important. Only one master, and obviously that may not work. This is kind of just logic off the top of my head. It looks like it'd work, and then. So here is where you could go through now and say if you have, so like if drive 1 is the master and it faults, the master drive in, and you get a fault, then you want to set. You want to do a set here, by the way, because if you do a regular coil, it will lock out that logic. So if you set it or reset it up at the top, like if there is a coil, a regular coil, because that coil is not active, it will override whatever's above it. And so if you use coils and not sets and resets, whatever the last coil is in your logic, that's going to be what executes. That is going to be the state no matter what. And sometimes that isn't very intuitive. So do this, and then we'll do the same thing, but for 2. So if drive 2 is the master, and this basically is your logic. And so now you're just swapping between the so the reason why this works is like our safety signals are not tied to the fault status. So that is very important to note, that when you're doing this, that out here we have our our inputs that should be our safety signals, that we will have like a like, here's our safety logic, whatever that is. Here's safety logic, and have all your e-stops, all of that stuff. And most people would say, hey, if our drive faults, stop it. Like, stop everything, stop the system. Well, if you want the drive to fault and then automatically swap over to being whatever, the only time that you would need to swap on a fault condition is if the drive that faulted was the master. And we're looking at kind of, that's what's going on here. So because if a following drive faults out, then it doesn't matter. So if it faults out, it stops pulling, that load is immediately transferred to the others, and it just it goes up. So one thing though that I guess, if you have a fault, it needs to trigger into an off 2. And so there's a parameter 2100 that you can change fault reactions, and make sure that that you haven't changed anything to like an off 3 in this situation, because if you got that fault, you get an off 3, and that generates braking torque, and so then it would start fighting the others. So kind of crazy, kind of like definitely a long live stream, 4 hours. This is my longest live stream, but yeah. So we have been. This is actually, though, a pretty fleshed out kind of changeover system. The only other thing that you would need now to kind of tie into some of this stuff would be the stuff like a safety circuit. So you have drive 1, drive 2, and so now, like, this seems pretty good because you're just putting in the actual drive telegram input, the drive telegram output, a system speed set point, which you could set from your HMI, pretty simple, or even a pot if you wanted to. You just have to scale that. Have your master torque value, which technically, I guess I do need to do one thing. This would not work. So, I'm going to insert this, and this is, by the way, I don't know why, but you can only insert, so we need to do the system control and pull it into OB1, right? Otherwise that master torque value isn't getting set. So and one thing, like in the system control as well, you could also have a line of something like this that says, if you, whoops, just thinking of, so like if neither of these is the master, you want to set, one of them as a master. You have to have a default master. Like, I mean, one of them has to be a master, and the other one can't be the master. There can only be one, but there has to be one. So that's basically it. I mean, there's a lot of stuff like in this kind of like load sharing, but that was a it was simple at first in my mind, but like as we start going through it, I mean, it's a good little application. So that was cool. So I will say, I thank y'all so much. And again, always these, I'm going to archive, make these archives. So, and I'm going to clean this one up. I'm probably going to break it down into one. I don't know. I'll probably just put this whole thing up there. But you have access to everything for the members. I will put this into the programmer level May archive. And again, for people that are getting in April and May, you are getting access to, or you're getting access to all of April and all of May. So those members that are joining in this month, you are getting access to everything that the April subscribers or the April members are getting as well. So just to make sure that you're always getting value for your membership. But yeah, so I'm gonna throw these up there, and yeah, hopefully it won't. It shouldn't be 2 weeks like it was this time. And we'll have a couple of cool. I know we've got questions about heart. I know we're going to finish up a Motion 102 class. I've got a safety and like how to do risk assessments and those sorts of things, like what's involved in a risk assessment, performance levels, SIL levels, those sorts of things that are involved in the CE mark that have some really good documentation, and we're going to do a whole class on that. So we've got a good month of May coming up. Hopefully I'll be able to do all of it, because starting up a system in Alabama next week, and trying to finish getting moving on a big system up in Indiana in towards the end of May. But hopefully I've got Starlink, and I will hopefully be able to keep doing these. I really appreciate everyone that joins in on these. I know Mondays, especially when they're this long, you come and go, kind of see what's going on, come in and hang out. And so I appreciate those that come on and join in. I always love the fact that there's so many people from all around the world that are able to get stuff from these videos. And yeah, I just really appreciate it. And so, as always, if this content was good, I mean, hit those thumbs up and subscribe, and join the Discord. This whole thing came from the help desk, and yeah, it was long. It's because it's basically 2 streams worth of stuff. So OG, thank you for your questions. It was a great thing, and hopefully I fleshed it out enough to where this application is able to be beneficial to you. But I appreciate everyone that has tuned in this week, and yeah, we look forward to the ones more in the future. And as always, keep learning, and yeah, keep going. I'll see you next time.